Our narrative tonight, it really unfolds from a pivotal moment in modern cosmology. This was a gathering, a true convergence of brilliant minds, held in the hallowed halls of Stanford University. It was March of 2003, and the air was crisp, both literally and intellectually. This intellectual summit, this meeting, bore a pretty evocative title: Universe or Multiverse? Think about that question for a second. Even in its simplicity, it really encapsulates one of the most profound dilemmas of contemporary physics. The very genesis of this significant event was sparked by the visionary impetus of Charles Harper. He represented the esteemed John Templeton Foundation. If you're not familiar with them, they're renowned for their generous patronage of inquiries that bridge the realms of science and those deep, profound human questions. So it was under their enlightened sponsorship that this crucial meeting truly took root. And so that's how this whole discussion got off the ground. Within the vibrant tapestry of this conference, the formidable task of shaping the scientific discourse fell upon the shoulders of two absolute giants in the field. First, Paul Davies, a physicist and writer whose explorations of the universe's ultimate questions have just captivated audiences worldwide. And then André Linde, a pioneering figure whose groundbreaking contributions to inflationary cosmology have fundamentally reshaped our understanding of the cosmos's earliest moments. Their shared vision guided the intellectual currents, ensuring the most pressing questions and promising research avenues were meticulously explored. Beyond that high-level intellectual scaffolding, there was also the intricate administrative ballet, right? The meticulous orchestration of every single detail that transforms a mere idea into a tangible event. That was masterfully handled by Marianne Myers of the Templeton Foundation. Her dedicated efforts ensured the seamless flow of discussions and the comfort of the assembled luminaries. This particular gathering, Universe or Multiverse, it arrived at what you could really only describe as a critical juncture in the burgeoning development of the subject itself. The very air was charged with anticipation, because the concept of multiple universes, once it was relegated to the fringes of speculative philosophy or science fiction, was beginning to assert its undeniable presence within the rigorous frameworks of theoretical physics. The discussions held, the papers presented, and the insights shared at Stanford, they represented the very cutting edge of this intellectual frontier. It was a privilege, honestly, to be entrusted with the monumental task of editing the resulting proceedings, to distill the rich essence of those deliberations into a coherent and accessible volume. Every single talk delivered at that landmark Stanford meeting is meticulously represented within the pages of this forthcoming book. It actually comprises approximately half of its total intellectual content. It's quite a lineup, right? These contributions, each of them a window into the mind of a leading expert, include chapters from the likes of James Bjorken, whose work delves into the fundamental definitions of universes; Nick Bostrom, who rigorously explores observation selection effects; Robin Collins, offering a unique theological perspective on the multiverse; and Paul Davies, with his characteristic blend of deep physics and philosophical inquiry; Savas Dimopoulos and Scott Thomas, probing the intricate links between particle physics and cosmology; Renata Kalosh, a key figure in M-theory and its cosmological implications; André Linde, illuminating the eternal tapestry of inflationary multiverses; Vyacheslav Mukhanov, offering profound insights into quantum cosmology and its interpretations; Martin Rees, a tireless champion of the multiverse concept and its astrophysical ramifications. You've also got Leonard Susskind, who vividly paints the vast and intricate string landscape, sure. Max Tegmark, classifying the hierarchical levels of multiverses. Alex Vilenkin, a pioneer in the concept of quantum creation of universes. And actually, my own secondary contribution, weaving another strand into this complex narrative. Each name, a beacon of intellectual endeavor, collectively contributed to a volume that would serve as a definitive snapshot of the field at that truly transformative moment. Okay, so several years prior, back in the gentle warmth of August 2001, another gathering, intimately connected in theme, had already sown some really important seeds. This earlier meeting, titled Anthropic Arguments in Fundamental Physics and Cosmology, unfolded in the historic and intellectually rich setting of Cambridge. Specifically, within the venerable home of Martin Rees. That intimate ambiance, it undoubtedly fostered a free exchange of ideas, paving the way for deeper insights. This Cambridge assembly also bore the subtle yet significant imprint of the Templeton Foundation's influence, as it was partially sustained by a grant. This particular grant, generously awarded to a collaborative quartet, myself, Robert Crittenden, Martin Rees, and Neil Turok, actually funded a broader project. It was thoughtfully named Fundamental Physics and the Problem of Our Existence. It was a profound undertaking, really seeking to connect the most intricate laws of the universe with the very enigma of our being. This specific award was just one thread in a larger tapestry of grants dispersed by the Templeton Foundation in the year 2000. It was all part of their ambitious cosmology and fine-tuning research program. A testament, really, to their enduring commitment to questions at the intersection of science and ultimate reality. Our collective decision, in the spirit of fostering vibrant intellectual exchange, was to judiciously utilize these funds to host a series of focused workshops. And the 2001 Cambridge meeting, therefore, holds the distinction of being the inaugural event in this illuminating series. Right, so that brings us to the thematic scope of that Cambridge meeting. It was, in a sense, a broader embrace than that of its Stanford successor. While Stanford honed its focus on the multiverse proposal itself, Cambridge cast a wider net, centering its discussions on the overarching anthropic principle. One might, with a certain intellectual elegance, consider the multiverse proposal as merely a particular, highly compelling interpretation or manifestation of the anthropic principle. Despite this broader thematic horizon, a significant portion, indeed, about half of the talks delivered at the Cambridge Assembly naturally gravitated towards the burgeoning multiverse theme. It was this inherent overlap, this fertile ground of shared inquiry, that really fueled my keen desire to ensure these invaluable contributions found their rightful place within the current volume. At the time, while I'd meticulously published a review capturing the essence of the Cambridge meeting in Physics World in October 2001, there hadn't been any formal, comprehensive publication of the individual talks. Recognizing the enduring significance of these discussions, I extended an invitation in 2003 to many of the distinguished Cambridge participants. I encouraged them to formalize their presentations into written contributions, albeit in updated form, reflecting any new insights or developments in the intervening period. My anticipation was met with profound satisfaction when nearly every invited scholar graciously accepted this invitation. Their collective contributions, rich in detail and intellectual rigor, now form the substantial remainder of this volume, seamlessly complementing the Stanford proceedings. Well, these deeply insightful chapters include the profound perspectives of John Barrow, a polymath who effortlessly bridges cosmology, mathematics, and philosophy; Brandon Carter, the very progenitor of the anthropic principle; and John Donahue, meticulously dissecting the fine-tuning problems of particle physics. Then there's George Ellis, offering a critical and rigorous philosophical examination of multiverse concepts; James Hartle, whose work illuminates the very quantum state of the universe; Craig Hogan, probing the delicate interdependencies of fundamental constants; Don Page, exploring predictions and tests within multiverse frameworks; Lee Smolin, offering compelling scientific alternatives to anthropocentric views; William Stuger, a unique voice at the intersection of science and theology; and Frank Wilczek, a Nobel laureate whose insights illuminate the very fabric of reality. Each name represents a pillar of thought, collectively constructing a comprehensive and multifaceted exploration. Our collective endeavor, fortified by the invaluable support of the Templeton Foundation, it extended beyond these initial gatherings. We meticulously organized 2 further meetings, Each was a unique exploration of related, yet distinct, facets of cosmic inquiry. The second of these intellectually stimulating assemblies, aptly titled Fine-Tuning in Living Systems, convened in the majestic and historically resonant setting of St. George's House, nestled within the ancient walls of Windsor Castle. It was August 2002, a sun-drenched month. The deliberate emphasis of this particular gathering shifted somewhat from the purely cosmological and physical, leaning more profoundly towards the intricate dance of biology. In this nuanced exploration, we were profoundly aided by the sagacious guidance of John Barrow, whose expansive intellect graced our program committee, ensuring a rich, interdisciplinary dialogue. While this meeting, in its own right, proved to be of immense and captivating interest, indeed, it perfectly encapsulated the rapidly burgeoning and increasingly vital area of astrobiology, the study of life in the universe. It yielded very little direct overlap with the central multiverse theme that underpins this current volume. Consequently, its rich discussions and findings aren't represented within these pages. However, it's important to note that the proceedings of that illuminating Windsor meeting found their own dedicated forum, having already been formally published as a special issue of the esteemed International Journal of Astrobiology in April 2003. Let's see. The third and final meeting in this funded series once again returned to the hallowed academic grounds of Cambridge, convening in early autumn, September 2005. It was, once more, graciously hosted by Martin Rees, though this time the intellectual hub was Trinity College. This was a location of even greater significance, given Martin's recent and distinguished appointment as Master of Trinity, a testament to his profound academic standing. The chosen title for this culminating assembly, Expectations of a Final Theory, vibrated with the grand ambition inherent in fundamental physics. The discussions at this meeting predominantly focused on the thrilling, often speculative, yet undeniably promising developments within the realm of particle physics. Particular emphasis was placed upon M-theory and the intricate string landscape scenario. These concepts, as we'll further explore, perhaps offer the most plausible and theoretically robust foundation for the very paradigm of the multiverse. Many of the talks, as is often the case at the vanguard of theoretical physics, were highly specialized. They delved into the abstruse mathematical and conceptual depths of these advanced theories. Given that this volume was, by this point, already on the precipice of going to press, it was, regrettably, too late to integrate these highly technical contributions into its already extensive framework. Right, so, nevertheless, two particular presentations stood out for their broad accessibility and profound generality. The introductory talk, delivered by the venerable Steven Weinberg, and the insightful summary talk by the brilliant Frank Wilczek. They beautifully complemented the articles already committed to this volume. It was, therefore, with immense delight that I received their affirmative responses, given at very short notice, a testament to their dedication to produce written versions of their talks for inclusion. The illuminating article by Stephen Hawking also originates from his compelling presentation at this same Trinity meeting. Though it bears mentioning, he had also previously contributed a talk at the earlier 2001 Cambridge gathering. So it's immensely gratifying to note that both of the Cambridge meetings, and by extension, all three of the intellectually vibrant gatherings generously supported by the Templeton Foundation, are indeed represented within the comprehensive intellectual scope of this volume. You know, although I've meticulously recounted the historical trajectory that ultimately converged to form this profound volume, it's crucial to emphasize something important. The articles contained within are organized not by the chronology of their original presentation, but by the inherent logic of their subject matter. Following the initial suite of expansive overview articles that collectively form Part 1, a thoughtful prelude designed to set the stage and introduce the grand themes, I've systematically divided the remaining contributions into three distinct, yet intrinsically interconnected categories. Part 2, with its deliberate focus, delves into the vast and intricate cosmological and astrophysical aspects of the multiverse proposal. Here, you're invited to contemplate the grand scale of existence, from the birth of galaxies to the ultimate fate of the cosmos, all seen through the lens of multiple realities. Moving seamlessly from the macroscopic to the microscopic. Part 3 gravitates towards concepts more intimately relevant to the cutting edge of particle physics and the enigmatic realm of quantum cosmology. This section explores the fundamental building blocks of existence and the very nature of quantum reality, questioning whether our universe is but one unfolding possibility among an infinite quantum foam. Finally, Part 4 broadens its embrace to address the more general and often deeply philosophical aspects that inevitably arise when contemplating the existence of multiple universes. This includes profound inquiries into the nature of scientific inquiry itself, the limits of human understanding, and the delicate dance between science and metaphysics. Now, of course, such a meticulously clean division, while conceptually useful, isn't strictly attainable in practice. Many of these profound articles, by their very nature, traverse and interweave more than one of these conceptual territories. Indeed, it's precisely this seamless amalgamation, this fertile cross-pollination of the cosmological perspective, with the insights gleaned from particle physics, which has most powerfully fueled the escalating interest in this captivating topic. Nevertheless, by and large, a careful and considered effort has been made to categorize the articles according to their predominant degree of emphasis, ensuring a logical flow through this intellectual landscape. It's noteworthy that while this book organically evolved from a curated collection of conference papers, the articles contained within are intended to resonate at a semi-popular level, accessible to an intellectually curious audience. Think of it as a discourse pitched at the intellectual altitude of publications like Science or Scientific American, demanding yet rewarding for the thoughtful layperson. Actually, a concerted effort was made to encourage most of the contributing authors to craft their contributions with this accessible intellectual horizon firmly in mind. However, it's an unavoidable truth that, given the diverse intellectual backgrounds and intricate specializations of our esteemed contributors, there's some natural variation in both the length and the inherent technicality of the articles. A few, indeed, more closely mirror the intricate technicality of their original conference presentations, delving into deeper mathematical or theoretical specifics. In instances where the papers lean towards a more technical exposition, I've taken it upon myself to elaborate at greater length in my own introductory remarks for those specific sections. This deliberate pedagogical intervention aims to bridge any potential gaps, making the profound insights contained within these more specialized contributions more readily accessible to a broader readership. In my considered view, the strategic inclusion of some of these more technical articles is not merely desirable but essential. It serves a crucial purpose: to unequivocally emphasize that the subject of the multiverse is, fundamentally, a proper and rigorous branch of science, firmly rooted in empirical observation and theoretical derivation, and not merely a realm of abstract philosophy or idle speculation. Furthermore, it's my sincere hope that this thoughtful blend of accessibility and rigor will broaden the book's appeal, drawing in both seasoned experts who seek nuanced detail and enthusiastic non-experts, eager to grasp the grand sweep of these cosmic ideas. So, as I alluded to in my more comprehensive introduction, the spectrum of reactions among scientists to the audacious proposal of the multiverse varies quite considerably. It is, to put it mildly, a concept that sparks fervent debate, with some even disputing whether it constitutes proper science at all. It is, therefore, absolutely imperative to underscore that this volume is emphatically not a proselytizing work. Its purpose isn't to convert, but to explore, not to assert, but to inquire. This nuanced stance is profoundly signified by the very question mark that punctuates its title. Indeed, I did briefly entertain alternative shorter titles, perhaps simply multiverse, or even more boldly, multiverse, without the question mark, implying an unshakable certainty. However, after careful deliberation, I ultimately discarded these alternatives as being too unequivocal, too declarative, in a field that thrives on open inquiry and unresolved questions. In truth, the distinguished authors who've contributed to this volume collectively display a remarkably broad range of attitudes towards the multiverse proposal. This intellectual spectrum stretches from ardent, almost zealous, support, through a thoughtful and open-minded agnosticism that embraces uncertainty, all the way to robust and well-reasoned opposition. While it's true that the proponents of the multiverse probably predominate numerically, and are certainly more extensively represented in the earlier sections of the book, particularly parts 2 and 3, which delve into the specific cosmological and particle physics models, a deliberate effort has been made to ensure intellectual balance. This equilibrium is meticulously restored in Part 4, where a significant number of the contributors articulate deeply skeptical perspectives, offering counter-arguments and alternative frameworks. Therefore, readers who persevere through the entire intellectual journey of this book, reaching its concluding pages, are unlikely to emerge sufficiently enlightened to definitively answer the profound question posed by its title. And perhaps that is precisely the point. Nevertheless, it's my fervent hope that they'll be profoundly stimulated by the rich diversity of views expressed, by the intellectual tension that arises from these contrasting perspectives, and by the sheer depth of thought brought to bear on this monumental subject. Finally, and perhaps most remarkably, it should be stressed that the most astonishing aspect of this entire book, a testament to the transformative shift in scientific thought, is that it unequivocally testifies to the sheer number of eminent physicists who now find the subject of the multiverse not merely interesting, but intellectually compelling enough to dedicate their precious time and formidable intellects to writing about it. It is, in retrospect, highly improbable, almost inconceivable, that such a volume, brimming with such a breadth of perspectives from such distinguished minds, could have been produced even a mere decade ago. This, in itself, speaks volumes about the evolving landscape of scientific inquiry. As the soothing voice continues, allow your thoughts to drift, gently carried by the unfolding narrative. This intricate tapestry of cosmic understanding, woven from the insights of leading minds, is designed to settle the mind, fostering a quietude that welcomes the natural descent into deep, restorative sleep. The very existence of this profound volume, a testament to collaborative intellectual endeavor, owes an indispensable debt to the myriad contributions from various individuals intimately involved in the 3 pivotal conferences upon which its foundation rests. First and foremost, and with a deep sense of gratitude, I must unequivocally acknowledge the profound and unwavering support of the John Templeton Foundation. This visionary institution not only served as the gracious host for the landmark Stanford meeting in 2003, providing the very intellectual arena for its groundbreaking discussions, but also played an instrumental role in financially underwriting and thereby making possible the 2 intellectually vibrant Cambridge meetings in 2001 and 2005. My personal indebtedness extends in particular to Charles Harper, whose initial spark of inspiration, whose keen intellect first conceived of this ambitious project and acted as its indefatigable initiator. Equally profound is my gratitude to his esteemed colleague Marianne Myers, who, as the distinguished director of the Humble Approach Initiative program, played the preeminent administrative role in the pivotal Stanford meeting. Beyond that, her meticulous and thoughtful oversight subsequently helped to navigate the intricate labyrinth of publishing, ensuring the smooth progress of this very volume from conception to realization. Special commendation, indeed, is also due to Paul Davies and André Linde, whose intellectual acumen and profound foresight guided the scientific program for the Stanford meeting. It was their collective genius that not only shaped the content of that seminal gathering, but also conceived the very title, Universe or Multiverse, a profound query that this book has inherited, serving as its enduring intellectual compass. The Templeton Foundation, with its expansive and subtle influence, indirectly yet powerfully, underpinned the Cambridge meetings. These pivotal gatherings were partly sustained through a significant Templeton grant generously awarded to a collaborative quartet, myself, Robert Crittenden, Martin Rees, and Neil Turok. It is with immense appreciation that I extend my thanks to my fellow grant holders for what proved to be a most stimulating and intellectually fertile collaboration. Their dedicated efforts undertook the lion's share of the demanding organizational work for the Cambridge meetings. This formidable team was further bolstered by the invaluable addition of David Tong, whose expertise joined the program committee for the culminating 2005 meeting, adding another layer of intellectual rigor. My gratitude is particularly profound for Martin Rees. Not only did he graciously host both of the Cambridge meetings, providing invaluable intellectual and personal space for their deliberations, but he also holds a singular place in my own intellectual journey. It was Martin nearly 30 years ago who first ignited my profound interest in this complex subject, gently nudging my thoughts towards these grand cosmic questions. And it was his persistent encouragement and unwavering support that ultimately spurred me to dedicate myself to the demanding, yet deeply rewarding, task of completing this extensive volume. My heartfelt appreciation also extends to the various dedicated individuals at Cambridge University Press, whose collective expertise and tireless efforts were instrumental in bringing this volume to fruition. Simon Kaplan, the discerning editor, initially commissioned this book, recognizing its nascent potential. John Fowler, another astute editor, subsequently made crucial editorial decisions, exhibiting remarkable diplomacy in navigating my numerous requests and ensuring the intellectual integrity of the work. The meticulous production editors, Jackie Burton and Bethan Jones, transformed the raw manuscript into its polished final form. And, with particular emphasis, I must acknowledge the extraordinary contribution of Irene Pitsey, the copy editor. She meticulously combed through the text, her keen eye suggesting countless improvements, refining prose, and ensuring clarity. Her remarkable patience in dealing with my continual stream of changes and revisions was nothing short of saintly, a testament to her dedication. Most indispensable of all, however, were the contributors themselves. It is to them that I extend my deepest thanks, not only for graciously agreeing to formalize their talks into written articles, but also for their enduring patience in responding to my numerous editorial inquiries, navigating the collaborative process with remarkable collegiality. Finally, my most profound gratitude is reserved for my dear wife, Mari, whose unwavering love, steadfast support, and remarkable patience enabled this demanding endeavor. Her understanding of my long hours spent immersed in the office, diligently working to finish this volume, was the silent, yet essential foundation upon which this entire project rests. As you absorb these dedications, feel the comfort of the words, allowing them to carry you deeper into repose. The intricate web of human collaboration, the meticulous care behind scholarly pursuits, mirrors the deeper cosmic structures we are about to explore. Let the soft cadences guide you now, further into the realm of tranquility. A subtle, yet profoundly significant point of clarification, crucial to navigating the intellectual landscape of this book, lies in the very terminology we employ. While the term universe has traditionally been embraced, almost universally, to denote the absolute totality of creation, everything that is, has been, or ever will be, the central theme, indeed the very pulse, of this volume is the audacious possibility that there could exist other universes. These hypothetical entities might manifest in various forms. Some perhaps causally connected to our own, albeit distantly, or in ways yet unimagined, while others might be utterly disconnected, realms entirely distinct from our known cosmos. A defining characteristic of these other realities is the potential for profound divergence. Within them, the very constants of physics that govern our existence, those immutable numbers that define the strength of forces, the masses of particles, the fabric of space-time, might assume different values. And, perhaps even more startlingly, the fundamental laws of nature themselves might operate under alternative formulations, leading to realities qualitatively unlike our own. The collective ensemble of these myriad universes, when contemplated as a whole, is often referred to as the 100G-verse. However, it must be acknowledged that this term, while widely used, isn't universally embraced by all. Indeed, within the very pages of this volume, you'll encounter several thoughtful alternatives, each attempting to capture a nuanced aspect of this grand concept. Terms such as megaverse, suggesting an even grander scale of existence, holocosm, implying a unified, all-encompassing whole, and parallel worlds, evoking a sense of coexisting yet distinct realities, are all employed by various authors. Right, so this delightful, yet sometimes challenging, lack of a universal consensus on the precise terminology is, upon reflection, hardly surprising. The concept of a multiverse isn't a monolithic idea sprung from a single source. Rather, it has arisen organically and indeed continues to emerge from a multitude of distinct and often independent contexts within the sprawling domains of modern cosmology, theoretical physics, and even the philosophy of science. Therefore, in my privileged role as editor, I deliberately refrained from attempting to impose any particular terminology, choosing instead to honor the intellectual autonomy of each author. I've consequently left contributors entirely free to employ whatever terms they deemed most appropriate and resonant with their specific arguments and perspectives. However, despite this overarching principle of authorial freedom, a singular, seemingly minor, yet ultimately crucial, pedantic issue did arise, necessitating a gentle imposition of uniformity. Insofar as most authors consistently utilize the word universe, albeit within varying conceptual frameworks, I endeavored to impose a consistent convention regarding its capitalization. While this might indeed appear to be a rather minor and perhaps even overly pedantic detail, I felt it incumbent upon a book titled Universe or Multiverse to at least acknowledge, and indeed to meticulously address, this potential source of ambiguity. This subtle distinction in notation, I believe, serves to clarify meaning and prevent potential misinterpretations. My adopted convention, meticulously applied throughout this volume, follows a clear and consistent logic. I've chosen to employ universe with an initial capital U when the author is, either explicitly or implicitly, proceeding under the assumption that our observable cosmos is the sole and unique totality of creation. This refers to the traditional, singular understanding of the universe. Conversely, when the author is, again either explicitly or implicitly, referring to a generic member of an ensemble of such entities, or perhaps merely to an abstract mathematical model that could represent any such reality, the term universe, with a small u, is consistently used. When specifically referencing the particular cosmic reality that we ourselves inhabit, the phrase, our universe, is the preferred descriptor. However, it's also acknowledged that the phrase, the universe, again with a capital U, is sometimes employed in this context, mirroring a similar convention within astronomical discourse. This mirrors, with elegant precision, the way in which astronomers refer to our galaxy as the galaxy, establishing a useful and intuitive distinction. This careful semantic differentiation allows, for instance, a clear conceptual separation between the visible universe, which specifically denotes the portion of our own individual universe that is currently accessible to our observational instruments and light cone, and the visible universe, which refers to the broader class of any potential universe, a part of which might be visible to us. As for the overarching concept, the word multiverse is, without exception, always spelled with a small m. This consistent lowercasing reflects the fundamental understanding that the idea of multiple realities arises in a variety of distinct and independent theoretical contexts. Consequently, it's entirely conceivable, indeed probable, that there could be more than one kind of multiverse, or even multiple realizations of the multiverse concept itself. It's worth noting, as a further layer of semantic complexity within this intricate field, that some authors, with their own nuanced perspectives, prefer to reserve the grand appellation universe, with a capital U, for the ensemble itself. In this specific usage, the term multiverse might then be retained for some hypothesized higher-level ensemble, a meta-multiverse, if you will. For instance, within the inflationary scenario, a concept we'll explore in greater depth, the term universe, might then be employed to describe the entire collection of expanding bubbles, rather than referring to any single, individual bubble within that vast cosmic foam. This intriguing semantic issue also surfaces prominently in the context of quantum cosmology, a field that implicitly, and often explicitly, assumes the profound implications of the many worlds interpretation of quantum mechanics. The established literature within this domain commonly refers to the wave function of the universe. However, upon closer philosophical scrutiny, one might persuasively argue that this wave function is, in actuality, being taken over a multiverse, a collection of coexisting, branching realities. Thus, the very title of this book, Universe or Multiverse, can be understood to pose not only the profound ontological question of whether other universes genuinely exist, but also the equally fascinating, albeit seemingly pedantic, etymological issue of precisely what we choose to call the ensemble of all that might be. This linguistic precision, subtle as it may seem, is fundamental to the clarity of our cosmic discourse. Let the words and their careful distinctions drift, as if on a gentle cosmic breeze, preparing your mind for deeper rest. The captivating image adorning the cover of this volume isn't merely an artistic rendering, but a profound visual representation of a complex mathematical construct at the heart of modern theoretical physics. It's a tri-dimensional depiction of what is, in reality, a quadridimensional Calabi-Yau manifold. This intricate geometric object holds immense significance within the framework of M-theory, the leading candidate for a unified theory of everything. The Calabi-Yau manifold specifically describes the geometry of the extra, internal dimensions, which are hypothesized to exist beyond the four familiar dimensions of space and time that we perceive. These curled-up, compact dimensions are thought to be too small to be directly observable, yet their precise geometry profoundly influences the properties of our macroscopic universe. The specific configuration of this Calabi-Yau manifold, in turn, relates directly to one particular string-inspired multiverse scenario, suggesting that the precise characteristics of our universe could be determined by the specific way these extra dimensions are compactified, with countless other compactification schemes leading to entirely different universes. And now, we transition into the first segment of our intellectual journey, aptly titled Part 1, Overviews. These introductory chapters are designed to provide a foundational understanding, setting the stage for the profound and intricate discussions that will follow. They offer a broad vista, a panoramic view of the conceptual landscape we're about to explore, ensuring that our collective understanding is firmly rooted before we delve into the more specialized details. Our journey into the multiverse begins with a sweeping introduction and overview, authored by Bernard Carr, hailing from the Astronomy Unit at Queen Mary, University of London. His words serve as a guiding light, illuminating the intricate path ahead. You know, nearly 3 decades ago, a seed of inquiry, profound in its implications, was planted. It was a seminal article, co-authored by myself and the esteemed Martin Rees, and published in the prestigious journal Nature in 1979. The very essence of that pioneering work was to meticulously gather, to synthesize, and to present in one coherent framework all the then-known constraints on the physical characteristics of the universe. This included the astonishing fine-tunings of the physical constants, those seemingly arbitrary, yet precisely calibrated, numerical values that govern the very fabric of reality. These were, even then, recognized as seemingly necessary for the miraculous emergence of life as we understand it. Such intricate constraints, these delicate cosmic balances, had been famously dubbed anthropic by Brandon Carter, drawing from the Greek word for man. Yet, even in those nascent days of the concept, it was beginning to be appreciated, and is now widely understood, that this descriptor is, in a sense, a misnomer. The profound fine-tunings, the exquisite precision of these cosmic parameters, bear no inherent or exclusive association with mankind in particular. Rather, they speak to the conditions necessary for the emergence of any form of complex self-organizing structure, indeed, for any potential for information processing and evolution within the cosmos. Right. So in that foundational article, we thoughtfully considered 2 distinct, yet interconnected, interpretations. First, there was the weak anthropic principle. This perspective accepts the laws of nature and the fundamental physical constants as given, as immutable bedrock, Within this framework, it posits that the very existence of observers, such as ourselves, then imposes a crucial selection effect upon where and when we, as observers, could possibly perceive the universe. It's a tautology, a self-evident truth. We must, by necessity, find ourselves in a region and at an epoch where the conditions allow for our existence. It offers no explanation for the constants themselves, but merely states that our observation is conditional upon them. Much more provocative, and indeed far more contentious, was the strong anthropic principle, at least in the sense that we employed the term. This interpretation suggested a deeper, more fundamental connection, that the very existence of observers imposes profound constraints, not merely on our location or time of observation, but on the physical constants themselves. It hinted at an underlying cosmic principle, a profound teleology, where the universe's parameters were, in some sense, preordained for the emergence of sentience. Well, in their early articulation, anthropic claims, particularly in their strong form, were often met with a degree of disdain, if not outright skepticism, by the prevailing community of physicists. This reaction, while perhaps softened over time, still persists in certain quarters today. While Martin Rees and I, in our seminal paper, cautiously advanced the view that any form of explanation for the observed fine-tunings, however tentative, was intellectually preferable to none at all, many within the scientific establishment regarded anthropic arguments as venturing beyond the legitimate boundaries of scientific inquiry. The very fact that some individuals of a theological disposition found in these claims compelling evidence for a creator, interpreting the strong anthropic principle as imbued with profound teleological significance, suggesting a universe purposefully designed, perhaps served to amplify this cautious, sometimes hostile reaction. However, and this is a crucial development in the intellectual landscape, attitudes have undergone a considerable transformation since those early days. This shift isn't primarily attributable to a fundamental change in the inherent status of the anthropic arguments themselves. As we'll see in a later chapter, some of these arguments have indeed grown stronger, fortified by new data and theoretical insights, while others have, perhaps, softened or become less compelling. Rather, the profound attitudinal shift stems from a fundamental re-evaluation of the epistemological status of the anthropic principle itself. This re-evaluation has occurred because cosmologists, through their relentless pursuit of a deeper understanding of the cosmos, have come to a startling realization. There are indeed many plausible contexts, deeply rooted in the evolving frameworks of theoretical physics, within which our universe could conceivably be just one member of a vast, possibly infinite ensemble of parallel universes. Within this grand ensemble, the fundamental physical constants, those very numbers whose fine-tuning we seek to explain, are free to vary. This overarching ensemble, this tapestry of coexisting realities, is what has come to be pervasively described as a multiverse. This term, indeed, is woven throughout this volume, forming the very core of its title. However, it must be stressed, as a point of intellectual honesty and precision, that many other terms are also employed, sometimes even interchangeably within the same conceptual context, reflecting the still evolving nature of this profound idea. These burgeoning multiverse proposals, in their initial conception, weren't generally motivated by a direct, explicit attempt to provide an explanation for the anthropic fine-tunings. Quite to the contrary, the vast majority of them emerged independently, as organic consequences of groundbreaking developments within the cutting-edge fields of cosmology and particle physics. They arose from internal logical necessities, from the relentless pursuit of theoretical consistency, and the elegant resolution of nagging puzzles. Nevertheless, as these theoretical frameworks matured, it became strikingly clear that the two concepts, the multiverse and the anthropic principle, are, in their deepest essence, inherently interlinked, almost inextricably so. For if, indeed, there exists a multitude of universes, a grand cosmic lottery of possibilities, then this naturally and compellingly begs the profound question of why we, as conscious observers, find ourselves inhabiting this particular one, with its seemingly exquisite and improbable balance of parameters. At the very least, one is compelled to concede that our own existence, our very capacity to observe and to question, functions as an undeniable and supremely relevant selection effect. Indeed, viewed through the lens of a multiverse, the necessity of our residence within one of the life-conducive universes becomes self-evident. This grand, overarching picture, in a stroke of elegant conceptual economy, effectively reduces the seemingly perplexing demands of the strong anthropic principle to a mere aspect, a subset, of the more straightforward weak anthropic principle. For this very compelling reason, a significant and growing number of physicists now regard the multiverse proposal as providing the most natural, indeed the most intellectually satisfying, explanation for the astonishing and otherwise perplexing anthropic fine-tunings observed in our cosmos. So, one of the most potent reasons for the burgeoning popularity of the multiverse proposal among the scientific community today lies in its apparent necessity for genuinely understanding the very origin of the universe itself. The traditional Big Bang model, while remarkably successful in describing the universe's evolution from a hot, dense state, remains tantalizingly silent on the conditions that preceded it, or the fundamental reasons for its initial state. The multiverse offers a potential escape from this primordial silence. Admittedly, within the expansive intellectual landscape of cosmology, there exist widely differing views and ingenious models regarding precisely how these different worlds might arise. Some innovative cosmological models, for instance, invoke scenarios in which our universe undergoes endless cycles of expansion and recollapse, a grand cosmic breath. In this cyclical dance, the fundamental constants, the very parameters defining reality, are hypothesized to be subtly altered or reinitialized with each cosmic bounce, each transition from contraction to expansion. In such a model, the different universes are not spatially distinct, but rather strung out sequentially along the axis of cosmic time, an eternal chain of evolving realities. Other prominent theories gravitate towards the inflationary scenario, a groundbreaking concept first proposed by Alan Guth. In this model, our currently observable cosmic domain, the vast expanse of galaxies and structures we perceive, is theorized to be but a tiny, relatively uniform bubble. This bubble, it's posited, underwent an extra-fast, exponential expansion phase during an incredibly brief epoch in the universe's earliest infancy. The crucial insight here is that, within this inflationary framework, our bubble is far from unique. Instead, the universe beyond our observable horizon, the meta-universe, is envisioned as containing many other such bubbles, each a distinct cosmic domain. A fascinating consequence arises. Each of these myriad bubbles could, in principle, possess different laws of low-energy physics, different sets of fundamental constants. In this inflationary interpretation, therefore, the different universes are spatially distributed, coexisting alongside each other, yet separated by vast, rapidly expanding regions of inflationary space. Extending this concept even further, two pioneering figures, Andrei Linde and Alex Vilenkin, independently yet convergently, invoked the profound idea of eternal inflation. In this even grander and more prolific scenario, each individual universe, once formed, is theorized to be continually self-reproducing, endlessly spawning new inflationary regions that in turn generate more universes. This eternal process predicts the existence of an infinite, or at least astronomically vast, number of such domains. And, crucially, within this ceaseless cosmic creation, each new domain could manifest with different coupling constants, different physical laws. In this most expansive view, the different universes extend not just in space, but also in time, a fractal explosion of coexisting, ever-generating realities. Yet amidst these diverse and compelling multiverse scenarios, there exists a contrasting perspective, championed by figures like Stephen Hawking. He favored a quantum cosmological explanation for the universe's origin, a framework rooted in the very principles of quantum mechanics applied to the cosmos as a whole. Hawking, notably, raised objections to the concept of eternal inflation, primarily on the grounds that it extends backwards into an infinite past. This, in his view, presented a fundamental incompatibility with his own seminal work, developed in collaboration with James Hartle, the no-boundary proposal for the origin of the universe. This audacious proposal posits that the universe, rather than emerging from a classical singularity or an infinitely old inflationary state, began at a finite time, but in a fundamentally quantum manner. The initial singularity, a problematic point in classical models, is elegantly regularized or smoothed out by requiring that time, in this primordial quantum realm, becomes imaginary. The no-boundary proposal suggests a universe that arises spontaneously from nothing, a purely quantum genesis. When employing the powerful path integral approach to calculate the probability of a particular cosmic history unfolding according to this proposal, a seemingly paradoxical result emerges. The initial conditions appear to favor very few expansion, E-folds, suggesting that the universe would recollapse far too quickly, long before the emergence of life, or indeed, any complex structure. However, it's precisely here that anthropic selection steps in, offering a vital salvage. The argument is that one only considers histories that contain observers. Thus, even if life-conducive histories are exceedingly rare within the quantum landscape of possibilities, our very existence guarantees that we must find ourselves in one of them, thereby providing a path for the no-boundary proposal to remain consistent with our observed reality. This particular approach to quantum cosmology, with its profound implications for the nature of reality, only truly makes coherent sense within the conceptual embrace of the many worlds interpretation of quantum mechanics. This revolutionary interpretation was originally proposed by Hugh Everett III in the 1950s, driven by an elegant yet radical desire to circumvent the problematic necessity of invoking the controversial collapse of the quantum mechanical wave function. This collapse, an essential feature of the standard Copenhagen interpretation of quantum mechanics, posits that the act of observation forces a quantum system from a state of superposition into a single, definite classical outcome. Everett's stroke of genius was to suggest that no such collapse truly occurs. Instead, our universe is theorized to continuously split or branch into multiple parallel realities every single time a quantum observation or interaction takes place. Consequently, one rapidly generates a vast, indeed astronomically huge, number of parallel worlds, each representing a different possible outcome of a quantum event. This profound concept, the many worlds interpretation, could legitimately be regarded as the earliest truly comprehensive multiverse theory, preceding many of the cosmological and particle physics-driven proposals. While one might intuitively desire to draw a clear distinction between these classical multiverses, those arising from cosmological processes or varying constants, and quantum multiverses, those arising from quantum branching, the astute Max Tegmark has compellingly argued that, at a fundamental level, there's no ultimate or absolute distinction between them. Both, in his view, represent different facets of a deeper underlying reality structured by mathematical possibilities. Quantum theory, as we know, emerged from humanity's persistent attempts to unravel and explain the enigmatic behavior of matter at the smallest scales, delving into the very heart of atoms and subatomic particles. This journey inward, a relentless probing of the universe's most fundamental constituents, has, in recent decades, led to equally astonishing developments in the realm of particle physics. These advances, in turn, have given rise to the widespread popularity of yet another distinct, yet interconnected, type of multiverse, the one born from the quest for a theory of everything. The holy grail of particle physics, the ultimate ambition that drives generations of researchers, is to discover a single, elegant, and comprehensive theory of everything, TOE. Such a theory would, ideally, unify all the known fundamental forces of physics, gravity, electromagnetism, the weak nuclear force and the strong nuclear force into a single, coherent, theoretical framework. Earlier attempts, models which successfully unified the weak, strong, and electromagnetic interactions, are commonly described as grand unified theories, xnoesis. While these xnoesis, despite their theoretical elegance, remain largely unverified experimentally, they've been a foundational part of theoretical physics for nearly 3 decades. Incorporating gravity, the most elusive of forces, into this grand unification scheme has proven to be an even more formidable challenge. However, in recent years, there have been exciting and promising strides, with superstring theory emerging as the currently favored, albeit still speculative, model for achieving this ultimate unification. Superstring theory itself isn't a monolithic entity. It exists in various versions, each offering a slightly different perspective on the fundamental nature of reality. Yet these diverse versions are, intriguingly, thought to be amalgamated or interconnected within a larger, more encompassing framework, famously termed M-theory. The historical expectation for such a theory of everything, particularly M-theory, was that, unlike the more limited, standard model of particle physics, which deliberately excludes gravity and contains several dozen seemingly arbitrary free parameters, M-theory would, conceivably, predict all the fundamental constants of nature uniquely. The dream was of a universe whose very parameters were precisely determined by the elegant, self-consistent mathematics of the ultimate theory, leaving no room for arbitrariness. That, at least, had been the fervent hope that fueled decades of research. However, recent, rather unsettling, developments within string theory, particularly its M-theory manifestation, suggest that this may, perhaps, not be the case. Instead, the number of possible stable or metastable theories, more accurately, distinct vacuum states or stable configurations of the quantum fields, that M-theory might admit could be astronomically enormous. Estimates range, staggeringly, to figures like 10 to the power of 500, or even higher. This bewildering multiplicity of possible vacuum states is sometimes vividly described as the string landscape scenario. If this scenario proves to be correct, then the long-cherished dream that all the constants of nature are uniquely and precisely determined by the ultimate theory would, regrettably, be dashed. Instead, there would exist a colossal number of possible universes, each corresponding to a different local minimum of the vacuum energy, each with its own unique set of physical constants. In this breathtaking vista, the specific values of the physical constants observed in our universe would then be contingent, that is, dependent entirely on which particular universe, or which specific valley in this vast string landscape we happen to occupy. Trying to predict the precise values of these constants from first principles in such a scenario would then become as forlorn and ultimately futile an endeavor as Johannes Kepler's earnest, yet ultimately misguided, attempts to predict the precise spacing of the planets in our own solar system based on the abstract properties of Platonic solids. The universe, in this view, would possess a deeper, more contingent, and perhaps less uniquely determined beauty. A profoundly crucial, indeed almost unsettling feature of this string landscape proposal is its direct implication for the nature of vacuum energy, which, in this context, would manifest itself as what is termed a cosmological constant. This cosmological constant, typically denoted by the Greek letter lambda, is a term that Einstein originally introduced into the field equations of general relativity. His initial motivation was to allow for a static cosmological model, a universe that neither expanded nor contracted, a notion he later famously rejected as his biggest blunder after Edwin Hubble's undeniable discovery of the universe's expansion. For many subsequent decades, cosmologists, despite a fundamental lack of understanding as to why, simply assumed that lambda was precisely zero. This assumption of a truly empty vacuum devoid of intrinsic energy, simplified their equations, and matched the then prevailing intuition. However, a truly remarkable and paradigm-shifting development occurred much more recently: the stunning discovery, confirmed by multiple independent lines of observational evidence, that the expansion of the universe is not only occurring, but is, in fact, accelerating. This cosmic acceleration, a profound and unexpected phenomenon, appears to be driven by the influence of what, at the very least, masquerades as a cosmological constant. One leading possibility for the origin of this enigmatic lambda is that it arises from the inherent quantum vacuum effects, the ceaseless, energetic fluctuations of quantum fields in empty space. The perplexing challenge, however, is that our current theoretical frameworks don't provide a reliable method to calculate these quantum vacuum effects with precision. And, perhaps more unsettlingly, the most natural theoretical value for this vacuum energy, based on simple dimensional analysis and the contributions of all known quantum fields, would be an absolutely gargantuan figure, equivalent to the Planck density, a value a staggering 120 orders of magnitude larger than the observed cosmic acceleration. Indeed, within the very framework of the string landscape proposal, one might intuitively expect the value of lambda to be distributed uniformly across the different universes, spanning a vast range from negative to positive values, potentially encompassing the immense Planck value. The observed value of lambda therefore appears not just small but implausibly, almost miraculously tiny in this theoretical context. Beyond the perplexing smallness of the cosmological constant itself, another layer of fine-tuning problem arises. The observed vacuum energy density is, in the current cosmic epoch, remarkably similar in magnitude to the matter density. This striking coincidence, however, is inherently time-dependent. In the early universe, matter density vastly dominated. In the distant future, if the acceleration continues, vacuum energy will utterly overwhelm matter. The near equality of these two densities, therefore, applies only at a particular, fleeting cosmological epoch, the very one in which we happen to exist. This cosmic coincidence further deepens the mystery. However, as first astutely pointed out by the venerable Steven Weinberg, the value of lambda is, crucially, constrained anthropically. His argument is simple yet profound. If the cosmological constant were significantly larger than its observed value, the repulsive force of vacuum energy would have caused the universe to expand so rapidly that galaxies and other gravitationally bound structures couldn't have formed. Without galaxies, there would be no stars, no heavy elements, and thus no life as we know it. While this anthropic explanation for the smallness of lambda isn't the only possible theoretical solution, there's a growing, albeit often reluctant, acceptance within the scientific community that it may well be the most plausible one. This intellectual concession is precisely why both the string landscape and the anthropic principle ideas have, in recent times, gained such widespread currency and intellectual traction. The crucial, and as yet unresolved, issue is whether the sheer number of vacuum states within the string landscape is sufficiently vast, and their distribution or spacing sufficiently fine-grained to rigorously satisfy these demanding anthropic constraints. This remains an active and vibrant area of theoretical inquiry. It must also be noted, as a fascinating digression that deepens the multiverse narrative, that M-theory, in its fundamental formulation, inherently requires the existence of dimensions beyond the familiar four of space and time that we perceive. Some of these extra dimensions are theorized to be compactified, curled up into incredibly tiny, unobservable loops, far smaller than the Planck length, so that we don't directly experience them. However, other scenarios suggest that some of these extra dimensions might be extended, potentially spanning vast distances. In such a scenario, our entire observable universe wouldn't be a self-contained entity, but rather a four-dimensional brain, a membrane-like structure, floating or embedded within a higher dimensional, bulk space. This brain world concept, first proposed by Lisa Randall and Raman Sundram, opens up entirely new and intriguing possibilities. In the initial versions of this brain world theory, the calculated cosmological constant was consistently negative, which, as we now know from observation, is fundamentally incompatible with the recently discovered accelerating expansion of our universe. However, just a few years ago, a pivotal theoretical breakthrough occurred. It was realized that M-theory solutions with a positive cosmological constant were also theoretically possible. This crucial development revitalized the collaborative efforts between cosmologists and string theorists, opening new avenues of inquiry. Moreover, the very notion that our universe might be a brain within a higher dimensional bulk naturally suggests yet another compelling multiverse scenario. If our universe is a brain, then there could conceivably be many other such brains, other universes, existing in parallel within the same higher dimensional bulk. These different brains, these parallel realities, could potentially be separated by vast distances within the extra dimensions, or perhaps even be in close proximity. Intriguingly, theoretical models have even posited that collisions between these various brains might serve as the very genesis of new universes, potentially generating the Big Bangs of the kind that initiated the expansion of our own cosmos. Indeed, some visionary theorists have even conceived of successive, cyclical collisions between brains, leading to endlessly cyclic models of the universe. It has even been claimed that this cyclical brain collision scenario could potentially provide an alternative, non-anthropic explanation for why the cosmological constant, lambda, naturally tends towards a value comparable to the matter density, thereby offering a different perspective on the cosmic coincidence problem. These are the profound and sometimes dizzying implications of the brain world paradigm. Allow the intricate details of these cosmic proposals to gently swirl within your mind as a cosmic lullaby. The possibilities are vast, and the connections profound, leading you ever closer to the peace of slumber. Let's now systematically place these astounding developments within a broader historical perspective, tracing the intellectual lineage that has led us to the audacious notion of the multiverse. We've thus far observed how a remarkable confluence of breakthroughs in both cosmology and particle physics has dramatically elevated the credibility of the multiverse proposal. But this concept, far from being a sudden apparition, is, in essence, the culmination of millennia of human inquiry. It represents the latest, most expansive chapter in humanity's ceaseless attempts to comprehend the physics governing the largest scales of existence, the cosmos, and the smallest scales, the fundamental particles. Because what we, at any given epoch, have regarded as the universe has been a constantly evolving concept, continuously reshaped and expanded as scientific progress relentlessly pushed the boundaries of observation, extending our gaze ever outwards to larger and larger scales, and ever inwards to smaller and smaller ones. In this relentless process of discovery, science has consistently unveiled new and intricate levels of structure within the world, from the vast cosmic web to the subatomic dance. Moreover, it has revealed fascinating and often unexpected connections between the fundamental laws operating at these vastly different scales, weaving a tapestry of interconnectedness that spans the entire spectrum of reality. This section, therefore, will serve not only as a historical review of this intellectual journey, but also as an opportune moment to revisit and clarify some of the basic yet profound ideas of modern cosmology and particle physics, thereby providing a reassuring intellectual foundation for those less familiar with these specialized domains. Our journey outward began with the most deeply ingrained of human intuitions, the geocentric view. Early humans, limited by their immediate perceptions and the apparent movements of the celestial bodies, naturally assumed that their very abode, the Earth, lay at the immovable center of the universe. Astronomical phenomena such as the daily arc of the sun or the nightly procession of stars were interpreted as being far closer and far more intimately connected to human experience than they actually were. This perspective was deeply intertwined with philosophical and theological beliefs. The heavens, in this ancient view, were the exclusive domain of the divine, a realm characterized by absolute perfection and unchanging regularity. The ancient Greeks, for instance, famously conceptualized the earth as residing at the motionless heart of a series of concentric crystal spheres. These ethereal spheres, carrying the celestial bodies, were believed to become progressively more perfect, more divine, as one moved outwards from the earthly realm. The outermost of these spheres was rigidly associated with the immovable stars, those fixed points of light that seemed to eternally adorn the night sky. Consequently, any transient phenomena, the fleeting streak of meteors, the mysterious appearance and disappearance of comets, were presumed to be of purely terrestrial origin, mere atmospheric disturbances, rather than celestial events. Even the fundamental laws of nature, such as the predictable regularity of the seasons, were, in this anthropocentric framework, seen as inherently human-centered, designed, in a profound sense, to be exploited for our own sustenance and purpose. It was therefore entirely natural, indeed almost inevitable, for early humanity to regard these regularities as direct and undeniable testimony to humanity's central, privileged role within the grand cosmic order. Then came the profound intellectual revolution of the heliocentric view, a paradigm shift that gently but firmly dislodged Earth from its perceived cosmic throne. In the pivotal year of 1542, Nicholas Copernicus, through his monumental work De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres, elegantly argued that a heliocentric picture, placing the sun, not the earth, at the center of the planetary motions, provided a far simpler, more harmonious, and mathematically more elegant explanation for the observed orbital paths of the planets. This audacious proposition, though not entirely new, it had been suggested much earlier by the Greek astronomer Aristarchus, albeit dismissed as blasphemous by most of his contemporaries, and by Nicholas de Cusa in 1444, who, with remarkable foresight, even argued that the universe had no single center and would appear the same from any vantage point, a precursor to the modern cosmological principle, fundamentally removed Earth from its assumed position of cosmic centrality. The intellectual seeds were sown. Further reinforcing this shift was the remarkable observation in 1572 by Tycho Brahe, a meticulous Danish astronomer. He meticulously documented a dazzling supernova in the constellation Cassiopeia. This new star dramatically brightened, then slowly dimmed over the course of a year. Crucially, its apparent position in the celestial sphere didn't change as the Earth moved in its orbit around the Sun. This unwavering position implied, with undeniable force, that the supernova was situated far, far beyond the sphere of the Moon, deep within the supposedly perfect and unchanging heavens. This observation directly contradicted the long-held Aristotelian view that the celestial realms were immutable. Consequently, Brahe's claim was initially met with deep skepticism and resistance, rooted as it was in centuries of established dogma. Frustrated by those who possessed the physical capacity to see, yet stubbornly refused to grasp the profound implications of what lay before their very eyes, Brahe, in the preface of his work De Nova Stella, penned a poignant lament. O crassa ingenia! O coecos coeli spectatores! O thick wits! O blind watchers of the sky! His words, a testament to the intellectual friction of paradigm shifts, resonate even today. The relentless outward journey of human understanding continued, culminating in the galactocentric view, a further expansion of our cosmic domicile. The next decisive step was taken by Galileo Galilei, a towering figure in the scientific revolution. Harnessing the power of the newly invented telescope, a marvel of contemporary technology, Galileo systematically demonstrated that not even the sun itself held a truly special or unique position. His meticulous observations of sunspots, those transient blemishes upon the solar disk, provided undeniable evidence that the Sun was not an unchanging, perfect celestial orb, but a dynamic, evolving star. Then, in the pivotal year of 1610, in his groundbreaking treatise, The Sidereal Messenger, Galileo advanced a truly audacious speculation that the faint milky band of light streaking across the night sky, then known simply as the Milky Way, but now recognized as our home galaxy, was, in fact, composed of an innumerable multitude of stars, each akin to our own Sun, yet situated at such unimaginable distances that they couldn't be individually resolved by the naked eye. This revelation not only cast profound doubt on the lingering vestiges of the heliocentric view's sense of unique centrality for our Sun, but also, in a single stroke, vastly increased the perceived size, the sheer immensity of the universe. An equally profound and perhaps even more foundational shift in our conceptualization of the universe unfolded a few decades later with Isaac Newton's monumental discovery of universal gravity. By elegantly linking the grand phenomena observed in the heavens, the orbits of planets, the fall of apples, to the seemingly mundane forces experienced on Earth, Newton utterly demolished the special, separate status of the celestial realms. The publication of his Principia Mathematica in 1687 ushered in the mechanistic view of the universe, a compelling paradigm in which the cosmos was, and often still is, regarded as a colossal, intricately designed and predictable machine. In the century that followed, the relentless development of increasingly powerful telescopes, coupled with the rigorous mathematical framework provided by Newton's laws, enabled astronomers to embark upon a systematic and increasingly detailed understanding of the intricate structure of the Milky Way itself. In 1750, Thomas Wright, a thoughtful English astronomer, boldly proposed that this luminous band was, in fact, a flattened disk of stars. This conceptualization paved the way for the profound speculation by Immanuel Kant in 1755, who, with remarkable prescience, posited that some of the fuzzy nebulae observed through telescopes were not merely diffuse gas clouds within our own star system, but rather island universes, vast stellar systems strikingly similar in structure and scale to our own Milky Way. This raised the tantalizing possibility that even our own majestic galaxy might not be unique or special in the grand cosmic scheme. However, despite these burgeoning insights, the galactocentric view, the deeply ingrained belief that the Milky Way constituted the entire universe, stubbornly persisted for several more centuries. Indeed, this remained the prevailing conviction, even for a mind as brilliant as Albert Einstein's, when he first published his revolutionary theory of general relativity in 1915 and began to apply its profound implications to the study of the cosmos as a whole. The universe, in his initial cosmological musings, was still a single, solitary galaxy. And then, the true expansion began, culminating in the cosmocentric view, a revelation that thrust our understanding of the universe to unprecedented scales. It was in the transformative decade of the 1920s that the prescient idea anticipated by Kant, the audacious notion that some of the nebulous patches of light observed through telescopes were, in fact, external to our own Milky Way, entirely separate island universes, began to truly take hold and gain intellectual currency. For a period, this profound question simmered as a matter of intense and passionate controversy within the astronomical community. A famous public debate in 1920 between Heber Curtis, who vigorously championed the island universe theory, and Harlow Shapley, who argued that our Milky Way encompassed all of existence, vividly encapsulated this intellectual tension. The definitive resolution to this contentious debate arrived in 1924, when the indefatigable Edwin Hubble announced his monumental discovery. Using the distinctive pulsating luminosity of Cepheid variable stars within the Andromeda Nebula, M31, he meticulously measured its distance, unequivocally demonstrating that it lay far, far beyond the confines of our own galaxy. M31 was, indeed, another island universe. An even more dramatic and paradigm-shattering revelation followed in 1929. Hubble, through painstaking observations, obtained radial velocities and reliable distance estimates for several dozen nearby galaxies. From this meticulous data, he made a truly astonishing discovery. Virtually all observed galaxies were not only moving away from us, but their speed of recession was directly proportional to their distance from us. This profound relationship is now universally known as Hubble's law, and its applicability has been rigorously demonstrated out to truly cosmic distances. It encompasses a region stretching 10 billion light-years from us and contains a staggering 100 billion galaxies. The most natural, indeed almost inescapable, interpretation of Hubble's law is that space itself is expanding, carrying galaxies along with it like raisins in a rising dough. This dynamic picture of an expanding universe had, remarkably, already been theoretically predicted in 1922 by Alexander Friedmann, based on his insightful solutions to Einstein's equations of general relativity. Friedmann's model strongly implied that the universe must have originated from a state of immense compression, an incredibly dense point in the distant past, at a time roughly equivalent to the inverse of the Hubble constant, a period now known to be approximately 14 billion years ago. This is the bedrock of the Big Bang picture, a cosmological model that received its most decisive empirical support in 1965, with the serendipitous discovery by Arno Penzias and Robert Wilson that the universe is pervasively bathed in a faint, omnipresent sea of background radiation. This cosmic microwave background radiation, or CMB, was subsequently found to possess a remarkably uniform temperature in every direction and to exhibit a perfect black body spectrum. This observational precision provided irrefutable evidence that the universe must, at some incredibly early epoch, have been sufficiently compressed and hot for matter and radiation to have been in thermal equilibrium, interacting intimately. Subsequent meticulous studies by the COBE-E satellite further confirmed the CMB's perfect black body spectrum, a triumphant validation that firmly established the Big Bang theory as a central, mainstream branch of modern physics. And now, our relentless outward journey brings us to the multiverse view, the most expansive and mind-bending conceptualization of reality to date. Further meticulous studies of the cosmic microwave background radiation, most notably by the WMAP Wilkinson Microwave Anisotropy Probe satellite, which precisely mapped the CMB's subtle temperature variations across the sky, have unveiled tiny, yet profoundly significant, temperature fluctuations. These minute ripples in temperature are understood to be the fossilized imprints of primordial density variations, the very seeds that, through gravitational instability over cosmic eons, eventually coalesced to form the galaxies and vast clusters of galaxies we observe today. The angular dependence and statistical properties of these ripples, as mapped with exquisite precision by WMAP, conform almost exactly to the predictions of the inflationary scenario. This suggests that our observable cosmic domain, with its remarkable uniformity and flatness, is merely a tiny, infinitesimally small patch of a much, much larger universe, a mere speck in a vaster cosmic ocean. This profound insight, derived directly from observational data, provided the first compelling evidence for what Max Tegmark, in his insightful classification, describes as the Level 1 multiverse. But the revelations didn't cease there. An even more dramatic and utterly unexpected discovery emerged from meticulous observations of distant Type Ia supernovae. These standard candles of the cosmos revealed, to the astonishment of cosmologists, that the expansion of the universe is not merely ongoing, but is, in fact, accelerating. While the precise cause of this cosmic acceleration remains one of the deepest mysteries in modern physics, the most compelling current explanation attributes it to a form of dark energy, most likely manifesting as a positive vacuum energy density. As we discussed earlier, the astonishingly low yet non-zero value of this vacuum energy density compared to theoretical expectations, hints strongly at the possibility that there exist many other universes, realms where the fundamental laws allow for different vacuum states. Consequently, this unexpected discovery of cosmic acceleration, and the vacuum energy that appears to drive it may well provide compelling, albeit indirect, evidence for Tegmark's more expansive, Level 2, multiverse, a universe of universes where fundamental constants themselves can vary. You know, this brief yet sweeping historical review of humanity's intellectual advancements on the outer front, the relentless expansion of our cosmological vista, powerfully illustrates a recurring theme. The longer and more deeply we have studied the universe, the grander and more immense it has consistently revealed itself to be. From a geocentric speck to a heliocentric dot, then a galactocentric island, and finally a cosmocentric bubble in an expanding sea, each scientific revolution has pushed the boundaries of our perceived reality. Indeed, from this perspective, the very concept of the multiverse might be regarded not as a radical departure, but as simply one more logical, perhaps even inevitable, step in this sequence of ever-expanding vistas, a natural progression opened up by the relentless march of cosmological progress.
While more conservative cosmologists might naturally prefer to maintain the traditional cosmocentric view, clinging to the comforting notion that ours is the sole and unique universe, the tide of intellectual history, with its consistent trajectory towards greater scale and diversity, perhaps suggests that the momentum is against them. The universe, it seems, is always larger, always more intricate than we initially dared to imagine. Okay, so now let's turn our gaze inward, embarking on an equally dramatic journey of perspective, the inward journey. Just as our understanding of the cosmos expanded outwards, so too did our comprehension of the universe's most fundamental constituents, delving deeper into the microscopic realm. This inward odyssey began with the advent of atomic theory in the 18th century, a groundbreaking intellectual leap that posited that all matter was composed of indivisible, fundamental units. This was followed by the startling discovery of subatomic particles at the dawn of the 20th century, revealing that even atoms were not elementary, but possessed an internal structure. And shortly thereafter, the revolutionary advent of quantum theory fundamentally reshaped our understanding of reality at its most granular level. The crowning achievement of this relentless inward journey is the profound revelation that everything in the universe, from the most colossal galaxy to the most ephemeral thought, is ultimately constructed from a mere handful of fundamental particles. Moreover, these particles, these ultimate building blocks, interact with each other through a mere quartet of fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Historically, these interactions were perceived as distinct and independent, each operating with its own unique strengths and characteristics. However, the relentless pursuit of a deeper, more unified understanding has led to the profound realization that some, and indeed possibly all, of these seemingly disparate forces can, at a deeper level, be unified as part of a single, overarching interaction. Figure 1.1, a visual metaphor, eloquently illustrates this grand narrative, suggesting that the entire history of physics can, in essence, be regarded as the relentless and triumphant history of this very process of unification. In the 19th century, the seemingly distinct phenomena of electricity and magnetism were elegantly woven together by James Clerk Maxwell's revolutionary theory of electromagnetism, revealing them to be but two facets of a single, unified force. Building upon this success, in the 1970s, the electromagnetic force was further combined with the weak nuclear force within the framework of the electroweak theory. This monumental achievement has since been rigorously confirmed by experimental data, standing as a testament to the power of theoretical unification. Theorists, driven by the relentless quest for deeper truths, have subsequently endeavored to merge the electroweak force with the strong nuclear force, aspiring to create a grand unified theory, GUT. While these guts, elegant as they are, still await definitive experimental verification, they represent a significant step towards a more comprehensive understanding. As we discussed earlier, in Section 1.1,
The ultimate and as yet incomplete step in this grand unifying vision is the audacious incorporation of gravity into this unified framework. This profound challenge is currently being tackled by the most promising theoretical candidates, string theory, and its more encompassing extension, M-theory. The very fabric of reality, it seems, is a symphony of interconnected forces. A truly remarkable and often counterintuitive feature of these advanced theories, particularly M-theory, is the radical proposition that the universe may possess more than the three spatial dimensions that we directly observe. It's hypothesized that these extra dimensions are compactified, curled up into incredibly small, unobservable loops, far beyond the reach of our current instruments, perhaps even as tiny as the Planck scale, a minuscule distance of 10 to the power of -33 cm, where the effects of quantum gravity become profoundly significant. Consequently, these hidden dimensions remain imperceptible to our senses and our experimental probes. In M-theory itself, the total number of dimensions, including time, is 11. The familiar four-dimensional physics that we experience is theorized to emerge from the intricate ways in which these additional dimensions are compactified, a process elegantly described by a complex mathematical object known as a Calabi-Yau manifold. The profound implication of this, the very discovery of these dark dimensions through the abstract reasoning of particle physics, shakes our conventional view of the nature of reality with a force as profound and unsettling as the astronomical discovery of dark energy through the observations of cosmology. Indeed, as we explored in Section 1.1, there may exist an intimate and deeply interconnected link between these seemingly disparate ideas, weaving together the largest and smallest scales of existence into a single, cohesive, and astonishing cosmic narrative. As you reflect upon these vast scales, both outwardly and inwardly, allow the profound scope of the universe to quieten your mind. Imagine the dance of dimensions, the unseen forces, leading you gently towards a deeper tranquility. Taken together, the relentless march of scientific progress on both the outer front, our expanding cosmological understanding, and the inner front, our deepening grasp of fundamental particles and forces, can, unequivocally, be regarded as a monumental triumph of human intellect and curiosity. In particular, the profound insights gleaned from physics have unveiled an astonishing underlying unity to the universe, making it strikingly clear that everything is interconnected in ways that would have seemed utterly inconceivable just a few decades ago. This profound and elegant unity, this cosmic harmony, is succinctly and beautifully encapsulated in the ancient archetypal image of the Ouroboros, the mythical serpent eternally eating its own tail, symbolizing cyclicality, self-creation, and the infinite. This evocative image, as depicted in Figure 1.2, adapted from a powerful visual originally conceived by the esteemed Sheldon Glashow, visually demonstrates the intimate and often surprising link between the macroscopic domain of reality, represented on the left side of the serpent's body, and the microscopic domain, represented on the right. The various pictures meticulously drawn around the graceful curve of the serpent represent the different, yet interconnected types of structure that pervade the universe, spanning an immense hierarchy of scales. Near the very bottom, anchoring our human perspective, are human beings themselves. As our gaze travels clockwise along the serpent's body, moving progressively to the left, we encounter successively larger objects, each a testament to the grand scale of cosmic organization: a majestic mountain, an entire planet, a blazing star, the intricate dance of a solar system, a colossal galaxy, a sprawling cluster of galaxies, and finally, encompassing all, the entire observable universe. The scale increases, step by step, towards the vastness. Conversely, as we follow the serpent's form clockwise, moving to the right from humanity, we delve into the microscopic realm, encountering successively smaller objects, each revealing deeper layers of fundamental structure: a complex biological cell, the intricate double helix of a DNA molecule, a foundational atom, the dense core of a nucleus, the elusive quark, the abstract realm of the grand unified theory, Guillotte scale, and ultimately, the infinitesimally small Planck length, the very boundary of. The numbers precisely annotated at the edge of the diagram vividly indicate the characteristic scale of each of these structures, expressed in centimeters, spanning an unimaginable range. As one seamlessly transitions clockwise from the serpent's tail to its head, the scale increases across an astonishing 60 decades of magnitude, from the smallest meaningful scale permitted by the laws of quantum gravity, a mere 10 to the power of -33 cm, to the colossal scale of the visible universe, a staggering 10 to the power of 27 cm. If one were to express these vast and minute scales in units of the fundamental Planck length, they would span from 0 to 60, transforming the Ouroboros into a kind of cosmic clock, where each minute on its dial corresponds to a breathtaking factor of 10 in scale. A further and profoundly insightful aspect of the Ouroboros diagram is subtly indicated by the horizontal lines that traverse its form. These lines symbolize the four fundamental interactions: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, and eloquently illustrate the subtle yet indispensable connections that bind microphysics to macrophysics. Consider, for example, the electric Quine-Tiny line. It elegantly connects an atom to a planet, because the very structure of any solid object, from the smallest pebble to the grandest celestial body, is fundamentally determined by atomic and intermolecular forces, both of which are, at their core, electromagnetic in origin. Similarly, the strong and weak lines forge an intimate link between a nucleus and a star. This is because the strong nuclear force, the incredibly powerful interaction that binds protons and neutrons together within atomic nuclei, is also the ultimate source of the immense energy released in the nuclear fusion reactions that power a star's incandescent brilliance. Concurrently, the weak nuclear force, responsible for processes like radioactive decay within nuclei, also plays a crucial, albeit subtle, role in the life cycle of stars, preventing them from burning out too quickly by regulating certain fusion pathways. Finally, the Guillotte line, a testament to the grand unified theories, connects the abstract grand unification scale, a realm of unimaginably high energies, with the formation of galaxies and vast clusters of galaxies. This profound connection arises from the Big Bang theory, which posits that the primordial density fluctuations, the very seeds of these colossal cosmic structures, originated at an incredibly early epoch, when the temperature of the universe was so extraordinarily high that the unifying Guillotte interactions were profoundly important, shaping the very fabric of nascent reality. Indeed, the Big Bang theory, in its most astonishing implication, suggests that these grand cosmic features arose when the current observable universe was compressed to the size of a mere grapefruit. The profound significance of the serpent's head meeting its tail lies in the astonishing notion that the entire universe, in its earliest infancy, was once compressed to a state of unimaginable density, classically to a point of infinite density, or, more rigorously and realistically, to the Planck density, the ultimate limit of physical compression. Given that light, the ultimate messenger of information, travels at a finite and immutable speed, our observational reach is fundamentally limited. We can never perceive beyond the distance that light has traversed since the Big Bang, a cosmic horizon stretching approximately 10 billion light-years from us. Consequently, increasingly powerful telescopes do not reveal new, untouched realms of the universe in the present moment, but rather allow us to probe deeper into the cosmic past, witnessing the universe as it was at successively earlier times. Cosmologists today possess a remarkably coherent and detailed picture of the universe's grand history, a chronological unfolding of cosmic events from its fiery birth. As we rewind the cosmic clock, galaxy formation, the coalescence of vast stellar islands, occurred approximately 1 billion years after the Big Bang. The cosmic microwave background radiation, the lingering afterglow of the Big Bang, last interacted intimately with matter a million years after the initial expansion. The universe's energy content was predominantly dominated by its radiant energy before approximately 10,000 years, a period when light particles and photons reigned supreme. Excess of matter over antimatter, a cosmic imbalance that ultimately allowed our existence. The electroweak unification, the merger of the electromagnetic and weak forces, occurred at a billionth of a second, a realm of energy that represents the highest energies currently probable experimentally in particle accelerators. Grand unification, the hypothesized merger of the strong and electroweak forces, and the epoch of inflation, the rapid exponential expansion, are believed to have occurred at an even earlier, more extreme time, 10 to the power of minus 35 seconds. And finally, the very beginning of the quantum gravity era, the smallest meaningful unit of time, was at an unimaginably fleeting 10 to the power of minus 43 seconds, the very edge of physical understanding. Perhaps the most striking aspect, the truly mind-bending connection, illustrated at the very top of the Ouroboros diagram, is its profound link with higher dimensions. On the microscopic side of the serpent, this arises from the fundamental tenets of various versions of superstring theory. All of these theories boldly posit that the universe possesses more than the three spatial dimensions that we directly observe. The intriguing hypothesis is that these extra dimensions are compactified, curled up into incredibly small, unobservable geometries. On the macroscopic side, the link to higher dimensions manifests because, as we have already discussed, some compelling versions of M-theory, the overarching framework for string theories, suggest that our universe could itself be a four-dimensional brane, a membrane-like structure, existing within a higher dimensional bulk space. This profound concept directly implies the possibility of a multitude of other branes, other universes, coexisting within the same higher dimensional bulk. It is crucial to remember, however, that even within these higher dimensional frameworks, there are other multiverse proposals that do not necessarily involve the existence of extra dimensions, demonstrating the rich and diverse landscape of possibilities within modern cosmology. Figure 1.2 also eloquently conveys a rich historical aspect, visually charting how humanity has systematically and relentlessly expanded the outermost and innermost limits of its cosmic awareness. Consider the trajectory. Primitive humans, limited by their immediate sensory perceptions, were acutely aware of scales ranging from approximately 10 to the power of minus 2 cm, the minuscule realm of mites observable to the naked eye, to 10 to the power of 7 cm, the colossal scale of mountains towering over their landscapes. By the 18th century, with the burgeoning of scientific instruments and methods, human awareness had expanded, encompassing scales from approximately 10 to the power of minus 5 cm, the microscopic world of bacteria, revealed by early microscopes, to 10 to the power of 17 cm, the vast expanse of the solar system, mapped by Newtonian mechanics and telescopic observations. And then, by the 20th century, propelled by the revolutions of quantum physics and modern cosmology, humanity's reach of awareness exploded, spanning scales from approximately 10 to the power of minus 13 cm, the infinitesimally small atomic nuclei probed by particle accelerators, to a staggering 10 to the power of 27 cm, the most distant galaxies, revealed by powerful telescopes and the expansion of the universe. It's truly striking to reflect upon the fact that science, through this relentless pursuit of knowledge, has already expanded the macroscopic frontier as far as is currently possible, reaching the very edge of the observable universe. While experimentally, we may never be able to directly probe much below the electroweak scale in the microscopic direction, the intellectual expansion has been profound. We might therefore most appropriately regard the Ouroboros, in its cyclical elegance, as representing nothing less than the blossoming of human consciousness itself, an ever-expanding awareness of the intricate wonders of the cosmos. As these grand concepts of scale and interconnectedness settle, allow your mind to expand and then gently contract, mirroring the cosmic breathing. Let the vastness lead to a feeling of profound calm, easing you into a state of deep relaxation. However, despite the burgeoning popularity of the multiverse proposal and the elegant theoretical frameworks that appear to give rise to it, it must be candidly admitted that a significant number of physicists remain deeply uncomfortable with this audacious concept. The reason for this discomfort is clear and, indeed, deeply rooted in the very ethos of scientific inquiry. The idea is, by its very nature, highly speculative. Furthermore, from both the grand perspective of cosmological observation and the intricate realm of particle physics experimentation, the very reality of a multiverse is, at present, fundamentally untestable. Indeed, a profound concern lingers. It may forever remain so in the most direct and tangible sense. Astronomers, with their ever more powerful telescopes, may never be able to directly observe these hypothesized other universes, separated as they are by vast cosmic distances, rapid expansion, or fundamental theoretical barriers. Similarly, particle physicists, with their colossal accelerators, may never be able to directly probe and observe the existence of the postulated extra dimensions, should they indeed exist, given their incredibly minute scales. The only conceivable pathway for direct empirical validation would arise if the effects of these hypothesized extra dimensions were to become visible or detectable at the TeV scale, the energy range accessible to current or near-future particle accelerators. In such a fortunate scenario, their existence might, in principle, be detected when the Large Hadron Collider, LHC, a marvel of engineering and scientific ambition, becomes fully operational. This would only be possible if, by some extraordinary cosmic alignment, these extra dimensions were as large as a millimeter, a macroscopic scale, compared to their theoretical Planck scale dimensions. However, it would indeed be an exceedingly fortunate coincidence, almost anthropically so, if the fundamental scale of quantum gravity just happened to align precisely with the largest currently accessible energy scale of our experimental probes. For these compelling reasons, a vocal segment of the physics community doesn't regard these multiverse ideas as falling under the legitimate purview of science at all. In their view, since our confidence in these concepts is currently predicated more on theoretical elegance, abstract faith, and aesthetic considerations, such as the mathematical beauty of a unifying theory, rather than on direct empirical experimental data, they contend that these ideas bear a greater resemblance to philosophical, or even religious tenets, than to rigorous scientific hypotheses. This skeptical viewpoint has been articulated forcefully and eloquently by distinguished commentators spanning a wide spectrum of metaphysical outlooks. Sheldon Glashow, a Nobel laureate, Martin Gardner, a renowned science popularizer and mathematician, and George Ellis, a distinguished cosmologist and philosopher, have all, from their unique perspectives, voiced strong reservations. Schumann O's. Indeed, Paul Davies, a physicist deeply attuned to the philosophical implications of cosmology, goes so far as to argue that the concept of a multiverse is just as metaphysical in its essence as the traditional theological concept of a creator who meticulously fine-tuned a single universe for our existence. At the very least, they contend, the notion of the multiverse inherently requires us to fundamentally expand and reevaluate our traditional idea of what legitimately constitutes science. You know, in the eyes of some, of course, the very discipline of cosmology has always precariously bordered on the realm of metaphysics, its grand pronouncements seemingly transcending direct empirical validation. Throughout its long and tumultuous history, cosmology has continually had to battle fiercely to prove its scientific respectability, often contending not only with entrenched religious dogmas, but also, paradoxically, with the cautious conservatism of scientific orthodoxy itself. For instance, a widely prevalent view that endured well into the 19th century, long after the heliocentric picture had firmly displaced the geocentric one, was that speculative inquiries about phenomena extending beyond the confines of our own solar system were simply not legitimate or proper science. This intellectual parochialism was vividly reflected in the pronouncements of Auguste Comte, a prominent French philosopher who, in 1859, confidently declared regarding the study of stars, "Never, by any means, will we be able to study their chemical compositions. The field of positive philosophy lies entirely within the solar system, the study of the universe being inaccessible in any possible science." Comte, however, with all his intellectual prowess, couldn't have possibly foreseen the imminent advent of spectroscopy, a revolutionary technique. This breakthrough was triggered by Gustav Kirchhoff's profound realization in the very same year, 1859, that the dark lines observed in the solar spectrum were, in fact, characteristic absorption features, uniquely associated with specific chemical elements. For the very first time, this allowed astronomers to probe, with unprecedented precision, the distant, seemingly unreachable, chemical composition of far-off stars, utterly disproving Comte's confident, yet ultimately flawed, prophecy. Cosmology, as a distinct and rigorous scientific discipline, truly began to attain its full status in 1915, a pivotal year marked by the advent of Albert Einstein's revolutionary theory of general relativity. This profound theoretical framework provided the subject with an unshakable and elegant mathematical basis, allowing for rigorous predictive models of the universe as a whole. The subsequent discovery of the cosmological expansion in the 1920s, spearheaded by Edwin Hubble's observations, then endowed cosmology with a firm and undeniable empirical foundation, anchoring its theoretical constructs to observable reality. Nevertheless, despite these foundational breakthroughs, it was many more decades before cosmology gained widespread, full scientific recognition. Consider, for example, the experiences of Ralph Alpher and Robert Herman, who, in the 1940s, were pioneering the theory of cosmological nucleosynthesis, the formation of light elements in the early Big Bang. They vividly recalled that, at the time, cosmology was then a skeptically regarded discipline, not worked in by sensible scientists. It was only with the accidental yet momentous detection of the cosmic microwave background radiation in 1965, the lingering afterglow of the Big Bang, that the hot Big Bang theory was decisively established as a legitimate and mainstream branch of physics, shedding its lingering aura of speculation. And it is only with the exquisite precision of recent results from the WMAP satellite, years after the Stanford meeting that inspired this book, that cosmology has truly blossomed into a quantitative science, capable of making real, testable, and highly precise predictions about the universe's evolution. Nevertheless, despite its remarkable journey to scientific maturity, cosmology still differs, in fundamental ways, from most other established branches of science. Unlike a laboratory experiment, one cannot, by definition, experiment with the universe itself. Its unique, singular nature presents inherent limitations. Moreover, many of the most profound cosmological speculations, particularly those concerning processes at the extremely early and unimaginably late times in the universe's history, depend crucially upon theories of physics, such as quantum gravity or string theory, which may, in practice, never be directly testable in a terrestrial laboratory. Because of these inherent challenges and conceptual distinctions, more conservative physicists still tend to regard certain cosmological speculations as venturing beyond the traditional domain of rigorous science. The introduction of anthropic reasoning into this already sensitive intellectual landscape, with its apparent dependence on our own existence, undoubtedly served to amplify this cautious, sometimes dismissive view. On the other hand, a growing number of physicists have consistently held a more positive and open-minded opinion towards these grand questions, recognizing their profound implications and the potential for new insights. Consequently, over the decades, a distinct polarization of attitudes towards the anthropic principle has developed within the scientific community. This intellectual tension is eloquently illustrated by contrasting quotes from prominent figures. The first, from the influential physicist Freeman Dyson, who, with a sense of profound connection, declared, "I do not feel like an alien in this universe. The more I examine the universe, and examine the details of its architecture, the more evidence I find that the universe in some sense must have known we were coming. This perspective, imbued with a sense of cosmic belonging, can be sharply contrasted with the view of the more antagonistic Heinz Pagels, who, with intellectual rigor, stated, "The influence of the anthropic principle on contemporary cosmological models has been sterile. It has explained nothing, and it has even had a negative influence. I would opt for rejecting the anthropic principle as needless clutter in the conceptual repertoire of science." Occupying an intellectually nuanced intermediate stance is Brandon Carter, widely regarded as one of the very fathers of the anthropic principle. He offered a more balanced view. The anthropic principle is a middle ground between the primitive anthropocentrism of the pre-Copernican age and the equally unjustifiable antithesis that no place or time in the universe can be privileged in any way. Carter's formulation suggests that while humanity is not at the geometric center of the cosmos, our existence undeniably places us in a privileged observational position, shaping what we perceive. Right, so the increasing popularity and theoretical robustness of the multiverse picture has, in recent years, significantly encouraged a pronounced drift towards Carter's more nuanced view. This is primarily because the multiverse conceptually offers a pathway for the anthropic fine-tunings to possess at least a quasi-physical explanation. While, to the staunchly hardline physicist, the multiverse might still appear somewhat speculative or lacking in full empirical respectability, it is, almost universally, regarded as intellectually preferable to explicitly invoking the concept of a creator as the direct explanation for cosmic design. Indeed, many anthropically inclined physicists, such as the influential Leonard Susskind and the venerable Steven Weinberg, are drawn to the multiverse precisely because it appears to elegantly dispense with the need for a God as the direct primary explanation of cosmic design. It offers a purely naturalistic framework for understanding the universe's apparent suitability for life. It's crucial, however, to caution that the dichotomy often presented, attributing anthropic fine-tuning solely to God or exclusively to the multiverse, is, in its essence, overly simplistic and intellectually limiting. While it's undeniably true that the observed fine-tunings, in their intricate precision, do not provide unequivocal, irrefutable evidence for the existence of a specific deity, neither would the confirmed existence of a multiverse, in and of itself, necessarily preclude the existence of God. As astutely emphasized by the philosopher and theologian Robin Collins, there is no logical impediment whatsoever to the notion that a creator, if such a being exists, might choose to act not through the direct, meticulous fine-tuning of a singular universe, but rather through the elegant and generative mechanism of a multiverse. A creator, in this view, could be the ultimate source of the laws and meta-laws that give rise to the entire cosmic ensemble. Nevertheless, it must be acknowledged that the multiverse proposal, by offering a compelling naturalistic explanation for cosmic suitability, certainly poses a serious intellectual challenge to traditional theological views that posit a singular, purpose-built cosmos. Consequently, it's hardly surprising that the multiverse concept has commended itself with particular appeal to atheists, serving as a powerful counter-argument to design inferences. Indeed, the philosopher Neil Manson, with a touch of provocative humor, has even famously described the multiverse as the last resort for the desperate atheists, highlighting its role in naturalistic explanations. By consistently emphasizing the scientific legitimacy and inherent intellectual rigor of both anthropic and multiverse reasoning, I don't for a moment intend to deny the profound relevance of these complex issues to the broader, enduring debate between science and religion. Indeed, the very existence of a multiverse, if empirically confirmed or theoretically robust, would undoubtedly carry immense religious implications, fundamentally altering our understanding of creation, divine action, and humanity's place in the cosmos. Consequently, insightful contributions from theologians, who have long grappled with such profound questions, are not merely important, but absolutely essential to a truly comprehensive discourse. More generally,
The discipline of cosmology, by its very nature, addresses the most fundamental and ultimate questions concerning the origin of matter, energy, space, time, and indeed, the very emergence of mind and consciousness. These are questions that resonate deeply with the core concerns of religion and philosophy. Therefore, it is imperative that theologians remain acutely aware of the evolving answers and insights that cosmology, through its scientific methods, continues to provide. Of course, the remit of religion, by its very definition, extends well beyond the purely materialistic and empirically verifiable issues that form the exclusive focus of cosmology. Religious truths often encompass moral, ethical, and spiritual dimensions that transcend the physical realm. Nevertheless, insofar as religious and cosmological truths overlap, and where they address common inquiries about the nature of reality, it is logically imperative that they must be compatible. This crucial point has been eloquently stressed by the cosmologist George Ellis, who judiciously distinguishes between cosmology, with a capital C, which in his expansive view takes into account the magnificent gestures of humanity, encompassing the broader human search for meaning and purpose, and cosmology, with a small c, which rigorously focuses solely on the physical aspects of the universe, its dynamics, and its material composition. In Ellis's profound perspective, the very essence of morality is, in some fundamental and deeply embedded way, woven into the intrinsic structure of the cosmos itself. Similar, deeply resonant ideas have been expounded by the philosopher John Leslie, who has meticulously explored the subtle connections between cosmic parameters and the possibility of ethical existence. On the other hand, it's equally important to acknowledge that science, by its very methodological constraints and empirical focus, cannot in itself directly deal with such deeply normative or metaphysical issues. It seems exceedingly unlikely that even in its most extended and expansive form, a form that might be required to coherently accommodate the concept of the multiverse, science will ever definitively prove or disprove the existence of God. Some individuals, through their personal interpretations of the physical world, may indeed perceive some subtle hint of the divine, or a glimmer of transcendent purpose. However, such subjective perceptions, as wisely articulated by the theologian and physicist John Polkinghorne, can only provide what he describes as nudge factors, gentle suggestions, rather than irrefutable scientific proof. Ultimately, deeply held convictions about God's existence must, surely, arise from an inside experience, an internal spiritual or philosophical realization, rather than solely from outside empirical revelations gleaned from scientific data. Even those eminent physicists who possess a mystical inclination, and whose profound insights grace the pages of this volume, do not usually base their personal faith on scientific discoveries or revelations, but rather on other, perhaps deeper, forms of knowing. For this very reason, it's important to understand that theology, in its explicit form, receives rather short shrift within the pages of this particular volume. The overwhelming majority of the contributors are physicists, scientists, deeply immersed in the empirical and theoretical exploration of the physical world.
And even those who, by their personal convictions, possess a theological disposition, have, almost universally, rigorously restricted their remarks and arguments to purely scientific considerations, ensuring that the discourse remains firmly within the established boundaries of empirical inquiry and theoretical physics. As the complexities of science and belief gently interweave, let your consciousness be carried by the flowing words, finding deeper and deeper rest in the profound questions that linger at the edges of our understanding. Now let's turn our attention to a concise yet illuminating overview of the book's structure, a roadmap for the intellectual journey that awaits us. Part 1, the very section we're now gently traversing, contains articles that directly derive from two pivotal talks delivered at a symposium bearing the evocative title, Expectations of a Final Theory. This gathering convened in the intellectually vibrant city of Cambridge, England, in September 2005. These contributions are meticulously placed at the very beginning of this volume, serving as exceptionally appropriate opening chapters. This is due to their inherent historical perspective, their capacity to contextualize the unfolding narrative of cosmic understanding, and crucially, because they vividly illustrate the dynamic way in which the subject of the multiverse has been powerfully propelled forward by a synergistic combination of groundbreaking developments in both cosmology and particle physics. Furthermore, the very act of commencing this volume with contributions from two distinguished Nobel laureates, titans in their respective fields, serves to unequivocally emphasize the remarkable degree of scientific respectability that this once marginalized topic has now demonstrably attained within the mainstream of fundamental physics. It underscores that these are not mere speculative musings, but serious inquiries at the forefront of cosmic understanding. In the very first contribution, titled Living in the Multiverse, the Venerable Steven Weinberg, drawing from his profound insights and based upon his opening talk at that seminal Cambridge meeting, articulates a compelling argument. He posits that the very idea of the multiverse represents nothing less than a truly significant change in the fundamental nature of science itself. It is, in his view, a radical and transformative shift in what we, as scientists, are prepared to accept as a legitimate and fruitful foundation for a physical theory. This profound epistemological shift, he meticulously explains, isn't a capricious intellectual whim, but is instead forcefully prompted by a compelling convergence of developments on both the theoretical and the observational fronts of modern physics. In particular, Weinberg powerfully highlights the anthropic constraint on the precise value of the vacuum energy or cosmological constant. This constraint, a concept he himself first astutely pointed out in 1987, decades before its observational confirmation, might legitimately be regarded as one of the very few truly successful anthropic predictions in the history of science. It provided a remarkable, if controversial, anticipation of a cosmic parameter's value based on the conditions for life. He further underscores the profound significance of the string landscape scenario, a concept we briefly introduced earlier. This intricate theoretical framework is, perhaps, the most plausible and robust theoretical basis for the entire multiverse proposal, offering a mechanism by which a multitude of distinct vacuum states, each corresponding to a different universe, might naturally arise. Indeed, this concept of the string landscape forms a central focus of several subsequent chapters within this volume, as various authors delve into its detailed implications. Complementing this, Frank Wilczek's contribution, aptly and poetically entitled Enlightenment, Knowledge, Ignorance, Temptation, is derived from his insightful summary talk delivered at the close of the Cambridge meeting. In this profound reflection, Wilczek delves into the rich historical and deep conceptual roots of the practice of reasoning about the fundamental parameters of physics and cosmology, particularly when such reasoning is based upon selection effects. He meticulously traces the intellectual lineage of these arguments, demonstrating how certain key developments have, over time, significantly improved the intellectual status and acceptance of such reasoning. Crucially, he emphasizes that these intellectual currents and their growing legitimacy predate the more recent developments in string theory, suggesting a deeper, more enduring foundation for these ideas. While Wilczek is acutely aware of the potential downside of this evolving intellectual development, perhaps a certain loss of predictive uniqueness or elegance in some theoretical frameworks, he nevertheless accepts it as an unavoidable part of the intellectual price that must sometimes be paid in the pursuit of a more comprehensive understanding of reality. He compellingly argues that such reasoning, rooted in selection effects, can and indeed should be thoughtfully combined with more traditional arguments based on the elegant principles of symmetry and the dynamic interplay of forces. It serves not as a replacement for these established methodologies, but as a vital and enriching supplement, offering new avenues of inquiry. This nuanced and profoundly insightful view is cogently encapsulated in Wilczek's eponymous classification of physical parameters, a framework that provides a clear intellectual map for navigating the complex interplay between fundamental constants, selection effects, and human understanding. Allow the gentle unfolding of these intellectual overviews to deepen your tranquility, guiding you towards the stillness of a profound and refreshing sleep. Now, let's transition into part 2 of our cosmic journey, a section dedicated to chapters whose emphasis lies primarily on the grand scale of cosmology and the intricate dance of astrophysics. This is where we explore the vast realms of spacetime, the formation of cosmic structures, and the fundamental forces that shape the universe, all seen through the lens of the multiverse hypothesis. The opening chapter in this profound section, titled Cosmology and the Multiverse, is authored by Martin Rees, a distinguished figure widely recognized as one of the foremost champions and eloquent articulators of the multiverse concept. As the gracious host of the 2 pivotal Cambridge meetings, both of which are significantly represented in this very volume, his insights are foundational. Rees begins by drawing our attention to a startling realization. The parts of space and time that are directly observable to us, even in principle, given the finite speed of light and the universe's age, may in fact constitute an infinitesimally small fraction of the totality of physical reality. This immediately poses a profound question. Should we, as scientists, summarily reject the unobservable part as a suitable subject for rigorous scientific discourse? Rees argues with compelling force that such a rejection, taken at the outset, is fundamentally unjustified. He eloquently elucidates that there exists a subtle and continuous transition, a slippery slope, as he vividly describes it, between what is immediately observable and what is, for now, seemingly unobservable. This blurring of boundaries suggests that our scientific inquiry should not be arbitrarily limited by our current technological or light cone horizons. After briefly, yet incisively, addressing some of the core conceptual issues inherent in defining and contemplating a multiverse, Rees delves into a fascinating hypothetical exercise. He discusses what our universe would be like, how radically different its structure and evolution might be if some of the key cosmological numbers, those fundamental parameters that define its properties, were altered. This thought experiment vividly illustrates the delicate, fine-tuning that appears to characterize our cosmos. Finally, and crucially for the scientific legitimacy of the multiverse concept, he explores how one might, in principle, devise tests for specific hypotheses about the underlying physics that could generate such a multiverse, offering a pathway, however challenging, for empirical validation. While the overarching focus of this volume is undeniably the grand concept of the multiverse, it's absolutely essential to recall and deeply understand the intricate, fine-tunings of cosmic parameters that the multiverse proposal, in its essence, purports to explain. Indeed, in the compelling absence of direct empirical evidence for the existence of other universes, these very fine-tunings, these astonishing coincidences, might legitimately be regarded as providing the most persuasive, if indirect, evidence for the multiverse's existence. This fundamental connection directly motivates the inclusion of my own chapter within this section, titled The Anthropic Principle Revisited. In this contribution, I meticulously re-examine the evolving status of some of the arguments that were originally presented in the seminal Nature paper I co-authored with Martin Rees in 1979. While my exploration does, at times, naturally veer into more expansive philosophical issues, I've strategically placed my chapter within this section because the vast majority of the anthropic relationships and constraints I discuss are intimately associated with the grand realms of cosmology and astrophysics. I lay particular emphasis on the crucial feature of these anthropic fine-tunings. They appear to be absolutely necessary for the intricate emergence of complexity during the universe's grand evolution from the initial Big Bang. The existence of conscious observers, such as ourselves, is then presented as merely one particular, albeit profoundly significant, manifestation of this overarching drive towards complexity, and may not, in itself, be the fundamental or ultimate point of the fine-tuning. The universe, in this view, is fine-tuned for complexity, and life is a natural outcome. Let the profound implications of cosmic fine-tuning and the potential answers of the multiverse gently guide your thoughts. Feel the sense of intellectual satisfaction that comes from exploring such grand questions, leading you towards deep and peaceful rest. Continuing our profound exploration within Part 2. Stephen Hawking, a mind of unparalleled brilliance, contributes a chapter titled Cosmology from the Top Down. In this insightful piece, Hawking offers a compelling contrast between differing approaches to the central, most profound questions of cosmology. These are the very questions that drive our quest for ultimate understanding. Why is the universe observed to be spatially flat and continuously expanding? Why, specifically, is it four-dimensional? 3 spatial dimensions plus 1 of time. Why did it begin with such incredibly small, yet precisely calibrated, density fluctuations, the very seeds of cosmic structure? And why, ultimately, does the intricate standard model of particle physics, with its myriad parameters, apply to our reality? Hawking then delineates the prevailing intellectual inclinations within the physics community regarding these questions. Some physicists, particularly those deeply immersed in the elegance and potential of string theory or M-theory, prefer to believe that these ultimate theories will, in their completeness, provide definitive answers to all these questions. Their hope is that these theories will uniquely predict the distinctive features of the universe, leaving no room for contingency or unexplained parameters. Others, perhaps more inclined towards a traditional teleological perspective, adopt the view that the initial state of the universe was precisely prescribed by an outside agency, often codenamed God. This implies a deliberate, purposeful design. A third perspective, increasingly gaining traction, is that there are, in fact, many universes, each with different properties, and that our particular universe is picked out from this vast ensemble by the anthropic principle, our existence shaping what we observe. Hawking, with his characteristic intellectual rigor, argues compellingly that string theory, in its current formulation, is unlikely to uniquely predict the distinctive features of the universe that we observe. Its vast landscape of possibilities, as we've discussed, suggests otherwise. But neither is he an advocate for a direct, teleological intervention by God as the primary explanation. Consequently, he firmly opts for the last approach, favoring a specific type of multiverse. This particular multiverse, in his view, arises naturally and almost inevitably within the context of his own groundbreaking work in quantum cosmology, where the very act of observation, in a sense, shapes the reality we perceive. Several other distinguished contributors to this volume resonate with Hawking's perspective regarding quantum cosmology as providing the most plausible and conceptually robust framework for the multiverse. Consequently, the book will naturally return to this profound theme later in its unfolding narrative. However, it's essential to recognize that the multiverse hypothesis, in its grand scope, manifests in many different guises, each with its own unique genesis and implications. These diverse conceptualizations are comprehensively and elegantly summarized in Max Tegmark's insightful chapter, aptly titled The Multiverse Hierarchy. Indeed, Tegmark, with his characteristic clarity, argues that the central and most compelling question is not merely whether parallel universes exist, but rather on how many fundamental levels they manifest. He meticulously demonstrates that physical theories which inherently involve parallel universes form a 4-level hierarchy, each level allowing for progressively greater diversity in the properties of these coexisting realities. Let's briefly unpack Tegmark's seminal classification. Level 1 is associated with the pervasive and continuous expansion of space, positing an infinitely large ergodic space. Within this boundless expanse, every conceivable initial condition for a Hubble volume, our observable universe, is, given enough space, eventually realized. This level of multiverse, astonishing as its implications are, is considered relatively uncontroversial by many cosmologists, as it is a natural and almost inescapable consequence of the well-established cosmological concordance model, which describes a flat, expanding universe. Moving to level 2, this level assumes that, given the same fundamental equations of physics, different vast regions of space can exhibit different, effective laws of physics. This implies variations not just in initial conditions, but in the values of physical constants, and even potentially in the dimensionality of spacetime or the specific particle content.
This arises, for example, from theories of inflation, where different regions settle into different fundamental states. Tegmark further subdivides Level 2 into 4 increasingly diverse sublevels. IIA involves the same effective laws, but different post-inflationary bubbles, essentially distinct Level 1 multiverses. IIB involves different local minima in the effective supergravity potential, leading to different fundamental parameters. IIC involves different fluxes, generalized magnetic fields, for a given compactification scheme of extra dimensions, leading to a vast number of vacuum states. IID involves entirely different compactifications of the extra dimensions themselves, leading to dramatically different fundamental particle properties and forces. Level 3 corresponds directly to the many worlds interpretation of quantum theory first proposed by Hugh Everett. In this profound view, every quantum measurement causes the universe to branch into multiple parallel realities, each representing a different possible outcome. Tegmark makes a fascinating and perhaps counterintuitive argument that the other branches of the wave function in Level 3 add nothing qualitatively new to the ensemble of universes already present in Level 2, meaning all possibilities are already covered. This is ironic, he notes, given that this level has historically been the most controversial and difficult for many to accept. Finally, at the pinnacle of this hierarchy is Level 4. This audacious concept invokes the idea that other fundamental mathematical structures themselves give rise to different fundamental equations of physics, implying that the very laws of nature could differ from universe to universe based on different mathematical foundations. Tegmark then bravely raises a crucial, deeply philosophical question. How, if at all, can these various multiverse models be empirically falsified, a cornerstone of scientific inquiry? He argues that a severe measure problem must be rigorously solved to make truly testable predictions at levels 2 through IV, a challenge that, as we shall see, is addressed in greater detail by later contributors to this volume. Tegmark's meticulous classification profoundly emphasizes the central and indispensable role of inflation, a theoretical postulate concerning an epoch in the very early universe when the expansion was dramatically accelerating. Inflation was originally invoked to elegantly explain two of the most striking and otherwise perplexing features of our observed universe: its remarkable smoothness, homogeneity, and isotropy on large scales, and its astonishing flatness, its spatial geometry being very nearly Euclidean. To many physicists, the theory of inflation, particularly in its eternal variance, still provides the most natural and robust theoretical basis for the multiverse scenario. Indeed, one of the prime advocates and a leading figure in exploring the anthropic aspects of inflation is André Linde. It is therefore most appropriate, and indeed essential, that he contributes the very next chapter, titled The Inflationary Multiverse. Linde begins by thoughtfully placing the anthropic principle within a broader historical context, tracing its evolution and reception within the scientific community. He acknowledges that while anthropic considerations possess the potential to significantly help us understand many of the peculiar properties of our world, for a considerable period many scientists felt a palpable sense of intellectual shame or discomfort in explicitly utilizing the principle in their rigorous research. This reluctance stemmed from a perception that it appeared too metaphysical, too teleological, bordering on non-scientific speculation. However, Linde powerfully argues that the chaotic inflationary scenario, a groundbreaking model that he himself pioneered and meticulously describes in his chapter, provides a simple yet profoundly compelling justification for the anthropic principle, offering a naturalistic framework for its application. He particularly favors the concept of eternal inflation, where the universe continuously self-reproduces, and thoughtfully links this to the latest, most cutting-edge developments in string theory, which provides a vast landscape of possible vacuum states. Linde then delves into the specific implications of this grand inflationary multiverse idea for three key cosmic puzzles: the nature of dark energy, the mysterious force driving cosmic acceleration, the abundance of relic axions, a theoretical particle candidate for dark matter, and the perplexing phenomenon of electroweak symmetry breaking, which gives mass to elementary particles. While these intricate implications are explored in greater detail in several subsequent chapters within this volume, Linde's article serves as an excellent, comprehensive introduction, skillfully weaving all these complex ideas into a cohesive and illuminating narrative. One of the intriguing issues explicitly raised by André Linde, and a persistent mystery in cosmology, is the pervasive prevalence of dark matter. This enigmatic substance, which interacts only weakly with ordinary matter and light, constitutes approximately 25% of the universe's total mass energy content. This profound mystery forms the central focus of a second, deeply insightful contribution by Frank Wilczek, titled A Model of Anthropic Reasoning, the Dark-to-Ordinary Matter Ratio. In this chapter, Wilczek meticulously zeroes in on a particular theoretical candidate for dark matter, the axion. The axion is a hypothetical elementary particle that arises from the theoretical mechanism associated with the breaking of Peccei-Quinn symmetry, specifically related to solving the strong CP problem in particle physics in the very early universe. Wilczek highlights a curious conundrum. In conventional axion cosmology, large values of the symmetry-breaking energy scale, which are intrinsically associated with large values of the Peccei-Quinn misalignment angle, a parameter that determines the initial energy stored in the axion field, are in principle forbidden. These large values would predict far too much axion dark matter, inconsistent with observations. However, a profound shift occurs if inflation, the period of exponential cosmic expansion, takes place after the breaking of Peccei-Quinn symmetry. In this scenario, remarkably, large values of the axion field's initial misalignment are theoretically permitted. This is contingent, however, on a crucial anthropic condition. We must inhabit a region of the multiverse where the initial misalignment of the axion field happened to be exceptionally small. While such life-conducive regions, where axion density is within an acceptable range, may occupy only a minute fraction of the total volume of the multiverse, if volume is the chosen measure, they are precisely the regions that would contain a disproportionately large fraction of potential observers. This is because regions with too much dark matter might not form galaxies suitable for life. This scenario, therefore, elegantly yields a possible, and indeed compelling anthropic explanation for the observed approximate equality of the dark matter density and the baryon, ordinary matter density in our universe. A coincidence that, from a purely particle physics perspective, appears otherwise perplexing and fine-tuned. We've already encountered another striking and profound feature of our universe. Its expansion appears to be unexpectedly accelerating, driven by the enigmatic influence of some form of dark energy. The precise source of this elusive energy remains one of the deepest mysteries in contemporary cosmology, but the leading candidate is a non-zero, cosmological constant. Indeed, as we've noted, one of the most impressive, albeit controversial, successes of anthropic reasoning is its potential ability to explain the present, surprisingly tiny, value of this cosmological constant. While several contributions within this volume touch upon this pivotal issue, the most comprehensive and rigorous treatment is meticulously provided by Alex Vilenkin, whose chapter, aptly titled Anthropic Predictions, The Case of the Cosmological Constant, offers a detailed review of the history, the intricate nature, and the implications of this particular anthropic prediction. Vilenkin, a pioneer in quantum cosmology, further discusses the inclusion of other potentially variable parameters, such as the elusive neutrino mass, and explores the broader implications of these anthropic considerations for the standard model of particle physics. In anticipation of a significant theme that emerges later in the book, Vilenkin emphatically stresses a crucial point. Properly formulated anthropic models, despite their inherent reliance on selection effects, can indeed yield rigorous, testable predictions. These predictions, while statistical in nature, can, in principle, be either confirmed or robustly falsified at a specified confidence level, thereby placing them firmly within the realm of legitimate scientific inquiry. However, he cautions that anthropic predictions inherently possess an intrinsic variance, a built-in level of uncertainty
which, unlike conventional experimental errors, cannot be indefinitely reduced, no matter how much theoretical precision or observational progress is achieved. This fundamental limitation is a defining characteristic of anthropic reasoning. The cosmological constant also plays a profoundly central role in James Bjorken's insightful chapter, The Definition and Classification of Universes. Bjorken, a distinguished theoretical physicist, begins with a fundamental premise. If the concept of a multiverse is to genuinely make scientific sense, then it is absolutely imperative to establish a specific, standardized, and rigorous definition for its individual member universes, particularly those that bear a strong resemblance to our own. Crucial to this precise description is the very definition of the size of a given universe. For the de Sitter model, a cosmological model characterized by a positive cosmological constant and exponential expansion, Bjorken astutely takes this size to be the asymptotic value of the inverse Hubble constant, a measure of the universe's ultimate expansion scale. This measure is directly and intrinsically related to the value of the cosmological constant itself, thereby ensuring that this enigmatic parameter plays a natural and central role in his proposed classification scheme. He further advances a bold hypothesis that the vacuum parameters and coupling constants of the standard model within any given universe are fundamentally dependent upon this size. Building upon this intricate framework, anthropic considerations then impose a crucial limit: the size of habitable universes, as we understand that concept, i.e., those capable of sustaining life, must, according to his calculations, fall within a narrow range, approximately a factor of 2, of our own observed universe's size. Bjorken then explores the profound implications of this intricate picture for understanding the perplexing hierarchy problem in the standard model, the astonishing disparity between the electroweak scale and the Planck scale. Finally, he delves into the broader and indeed fundamental issues of falsifiability and verifiability as they pertain to such grand cosmological constructs, rigorously examining how these theoretical frameworks might be empirically tested. Bjorken, in his rigorous analysis, doesn't explicitly attempt to provide a fundamental physical basis for models characterized by different cosmological constants. However, a compelling and plausible theoretical motivation for such variations arises directly from the cutting-edge frameworks of string theory, or its more encompassing extension, M-theory. This intricate connection is thoughtfully discussed by several contributors throughout this volume. Nevertheless, the most thorough and illuminating discussion of the cosmological applications of this profound idea is meticulously provided in Renata Kalosh's highly technical yet profoundly important chapter, M/String Theory and Anthropic Reasoning. In this contribution, Kalosh, a leading figure in M-theory research, outlines some of the most recent and groundbreaking cosmological studies that directly engage with M/string theory. She then presents a couple of illustrative examples where anthropic reasoning, that powerful lens through which our existence shapes our understanding of cosmic parameters, when judiciously combined with our current, albeit incomplete, theoretical understanding of string theory and supergravity, proves remarkably helpful in shedding light on the mysterious properties of dark energy. This is a rather technical article, indeed, delving into the intricate mathematical and conceptual details of advanced theoretical physics. However, its importance cannot be overstated. It describes, with intellectual rigor, the seminal results of her famous collaborative paper with A. Linde, S. Kochru, and S. Trivedi, a work that provided a profound breakthrough. This paper demonstrated that M/string theory, contrary to earlier assumptions, can indeed admit models with a positive cosmological constant. This was a truly crucial development because, for a considerable period, string theorists had generally assumed that the cosmological constant, if non-zero, would necessarily have to be negative, a prediction directly contradicted by astronomical observations. Thus, Kalosh's work provides a compelling example of how profound insights and unexpected breakthroughs in cosmology have, in turn, led to crucial revelations and advancements within the intricate realm of particle physics, demonstrating the deep interconnectedness of these seemingly disparate scales of inquiry. Allow the profound implications of string theory and its cosmic connections to settle in your mind, weaving a complex and fascinating tapestry. Let the intellectual depths guide you into a state of deep, undisturbed rest. Closely and intricately related to the profound themes explored in Kalosh's chapter is the final contribution in Part 2, authored by the distinguished Savas Dimopoulos and Scott Thomas, titled The Anthropic Principle, Dark Energy, and the LHC. In this compelling analysis, they advance a significant argument that, within a broad and encompassing class of theoretical frameworks, anthropic reasoning itself leads to the prediction of a time-dependent vacuum energy, a form of dark energy that evolves over cosmic eons and which exhibits distinctive and potentially observable characteristics. The most exciting and tantalizing aspect of this profound proposal is its direct implication for experimental verification. It yields predictions that might, in principle, be testable with the Large Hadron Collider, LHC. The LHC, a colossal marvel of engineering and scientific ambition, was due to commence its groundbreaking operations in 2007, ushering in a new era of high-energy physics. This direct connection between the vastness of cosmic dark energy and the intricate realm of particle accelerators vividly illustrates the intimate and indispensable link that now exists between cosmology and particle physics. This natural intellectual bridge smoothly leads us into the very next part of this volume, which will deliberately shift its focus to the intricate particle physics aspects of the multiverse hypothesis, exploring how the fundamental constituents of reality might influence and be influenced by the existence of myriad other universes. Our journey now carries us into Part 3 of the volume, an exploration that delves into the intricate realm of particle physics and quantum theory. This section thoughtfully begins with two illuminating articles that meticulously dissect the enigmatic values of the fundamental constants that govern particle physics, probing their origins and implications. Following this, the narrative gracefully transitions to explore the profound and often surprising links between these microscopic realms and the grand framework of string theory, a leading candidate for a theory of everything. This section then culminates with a series of deeply conceptual articles that are concerned with the very foundations of quantum theory itself. This is a deliberate and crucial structure, as there is a profound, twofold connection with quantum theory that underpins much of the multiverse discussion. Firstly, the many worlds interpretation of quantum mechanics, a radical and elegant concept, provided one of the very earliest and most influential multiverse scenarios. Indeed, it corresponds directly to Max Tegmark's Level 3 classification. Secondly, and equally important, the emerging field of quantum cosmology, which seeks to apply the principles of quantum mechanics to the universe as a whole, is most naturally and coherently interpreted within the framework of this very proposal, offering a tantalizing glimpse into the quantum genesis of cosmic reality. That the collective, wave function of the multiverse can, in its vast and intricate unfolding, explore a multitude of diverse vacua, each representing a distinct stable configuration of fundamental fields, characterized by differing symmetries and unique sets of physical parameters, serves as the compelling starting point for Craig Hogan's insightful chapter, Quarks, Electrons and Atoms in Closely Related Universes. In the intricate context of such theoretical models, where the universe's fundamental properties are not uniquely fixed but arise from a vast landscape of possibilities, Hogan astutely points out a crucial implication. He argues that the properties of universes closely related to our own, those differing only by subtle shifts in fundamental parameters, can be profoundly understood by meticulously examining the consequences of even small departures of these physical parameters from their observed values. He focuses his rigorous analysis on the fundamental masses of the light fermions that constitute the very stable matter of which we, and indeed all complex structures, are composed, the up and down quarks, and the electron. Hogan's meticulous calculations reveal that the observed values of these masses reside within an astonishingly narrow window. This precise calibration isn't arbitrary. It's the very condition that allows for the existence of a rich variety of stable atomic nuclei beyond mere protons. Crucially, it also permits atoms to form with stable shells of electrons, preventing them from being violently devoured by their own nuclei. Given that any living world, any realm capable of supporting complex molecular structures, fundamentally necessitates the existence of stable nuclei, beyond the bare simplicity of protons and neutrons, these precise fundamental parameters of the Standard Model emerge as compelling candidates. Their values, in this view, are not uniquely derived from fundamental theory, but are rather determined through intricate selection effects operating within the grand tapestry of a multiverse. Hogan further emphasizes another tantalizing and potentially observable link with reality. He speculates that if the precise values of these fundamental fermion masses are, in fact, fixed by the large-scale processes of brane condensation or the specific compactification of extra dimensions, cosmic events unfolding in the early universe, then this profound branching event might leave an observable, fossil, or imprint. This fossilized signature could manifest as a distinctive, gravitational wave background, a faint cosmic hum permeating space-time, detectable by future generations of gravitational wave observatories. Such a discovery would provide a direct empirical window into the very processes that shaped the fundamental constants of our universe. In the second chapter of this section, titled The Fine-Tuning Problems of Particle Physics and Anthropic Mechanisms, John Donahue, a distinguished particle physicist, offers a compelling and illuminating perspective. He emphasizes that many of the classic and most perplexing problems of particle physics, those long-standing puzzles that defy straightforward explanation, appear in a radically different, and indeed far more soluble, light when viewed through the profound lens of the multiverse. Donahue meticulously explains the concept of fine-tuning within the rigorous framework of particle physics. Parameters are deemed fine-tuned if the magnitude of the quantum corrections, the subtle yet pervasive influences of quantum fluctuations, to their values, as calculated in perturbation theory, are far larger than their bare or initial values. This implies a seemingly unnatural, almost miraculous cancellation between these two vastly different numbers to yield the observed tiny result. Donahue then highlights three specific parameters within the Standard Model that are particularly puzzling due to their unnaturally small values. Two of these, the Higgs vacuum expectation value, the fundamental field that gives mass to elementary particles, and the cosmological constant, the vacuum energy density of spacetime, constitute what are widely recognized as the two great fine-tuning problems that pervasively motivate much of the research in theoretical particle physics. The third perplexing parameter is the strong carbon monophosphide violating factor, also known as the theta parameter, which we previously encountered in Frank Wilczek's second contribution, a quantity whose astonishingly small value hints at deep, unexplained symmetries. Donahue argues, with compelling logic, that all of these apparent fine-tunings are elegantly alleviated, indeed almost naturally explained, when one meticulously accounts for the anthropic constraints that would inherently exist within the framework of a multiverse. If only universes with specific tiny ranges of these parameters can support life, then our observation of these values becomes not a coincidence, but a selection effect. However, Donahue wisely cautions that the formidable challenge remains to construct a realistic, rigorously formulated physical theory of the multiverse, one that can generate this vast array of parameters, and, even more crucially, to devise empirical tests for it. He then thoughtfully describes some intriguing phenomenology, observable patterns, within the masses of quarks and leptons. These subtle patterns, he suggests, may potentially provide a vital window onto the underlying multiverse theory, offering a pathway for its experimental validation. The primary reason why particle physicists have, in recent times, become so profoundly interested in the audacious multiverse proposal lies in a series of groundbreaking and often unsettling developments within string theory. In particular, the tantalizing possibility that M-theory, the overarching framework for string theories, may naturally lead to an astronomically vast number of distinct vacuum states, each of which, in essence, could be associated with a different possible universe, possessing its own unique set of physical laws and constants, is a profoundly crucial feature of Leonard Susskind's revolutionary string landscape proposal. In his deeply insightful chapter, The Anthropic Landscape of String Theory, Susskind, a leading architect of this concept, offers what he describes as educated guesses about the intricate topography of this string theory landscape of vacua. Drawing upon the recent, groundbreaking work of a multitude of pioneering authors, he powerfully argues that this landscape could be unimaginably vast and astonishingly diverse, encompassing a bewildering array of cosmic possibilities. He contends that, whether we find it aesthetically pleasing or not, this inherent multiplicity and diversity of the string landscape is precisely the kind of behavior that fundamentally lends credence and intellectual necessity to the anthropic principle. Susskind then meticulously discusses the complex, theoretical, and profound conceptual issues that inevitably arise in a cosmology that is explicitly based on the inherent diversity of environments implicit within string theory's vast landscape. While some of the later stages of his exposition do delve into rather technical details, accessible to those deeply immersed in the intricacies of string theory, these ideas are of fundamental and paramount importance to the overarching narrative of this volume. Indeed, Susskind's chapter, having been available in preprint archives for several years, stands as one of the most widely cited and influential papers in this rapidly evolving field, a testament to its profound impact on our understanding of the universe's possible architecture. As we have repeatedly stressed throughout this narrative, the many worlds interpretation of quantum theory, first proposed by Hugh Everett, provided one of the very earliest and most radical versions of the multiverse scenario. This profound concept is particularly relevant and indeed almost indispensable to the field of quantum cosmology, which, as a discipline, is most naturally and coherently interpreted in terms of this very proposal. This compelling viewpoint is advocated with remarkable cogency and intellectual clarity in quote, Cosmology and the Many Worlds Interpretation of Quantum Mechanics by Vyacheslav Mukhanov. Indeed, Mukhanov argues with persuasive force that the very wave function of the universe, the quantum description of the cosmos as a whole, and the specific patterns of cosmological perturbations, the tiny fluctuations that later grew into galaxies, generated by inflation, can only be truly understood and made sense of within the elegant yet radical framework of Everett's interpretation of quantum mechanics. He acknowledges that the main reason why Everett's interpretation has not been taken seriously by a significant portion of the physics community is its seemingly unpalatable prediction that we, as individual conscious beings, each have an unfathomable number of parallel copies of ourselves, existing in myriad branching realities. However, Mukhanov counters this discomforting implication by arguing that these quantum copies are not, in any practical or existential sense, dangerous or threatening. This is because, due to the fundamental principles of quantum mechanics, we cannot even in principle communicate with them or directly perceive their existence. Our reality, in this view, remains stubbornly isolated within its own branching path. The intricate and profound link between Everett's visionary picture and the broader multiverse proposal is further probed and elucidated in depth by Brandon Carter, the very progenitor of the anthropic principle. His chapter, Microanthropic Principle for Quantum Theory, while admittedly somewhat technical in its exposition, is exceptionally valuable. It provides not only an excellent and meticulously detailed historical perspective on the evolution of quantum interpretation, but also leads to a powerful and refined interpretation of the many worlds picture that transcends the original seminal version proposed by Everett. Carter traces the intellectual lineage,
noting that probabilistic models, meticulously developed by pioneering thinkers such as Ludwig Boltzmann upon the foundational insights of figures like Thomas Bayes, were, for a long period, commonly regarded as mere approximations to an underlying, fundamentally deterministic reality. However, this deeply ingrained view underwent a radical reversal with the revolutionary advent of quantum mechanics, under the intellectual leadership of Werner Heisenberg and Paul Dirac. From that transformative moment forward, it was the deterministic description that was relegated to the status of an approximation, an emergent property, from a more fundamental probabilistic reality. In this new quantum paradigm, the role of the observer became particularly prominent and perplexing. In Carter's insightful view, the fundamental lack of objectivity inherent in the original Copenhagen interpretation of quantum mechanics has not, to this day, been satisfactorily resolved by newer approaches, even those of the kind pioneered by Everett. He contends that the core deficiency of such interpretations is directly attributable to their failure to adequately account for the anthropic aspect of the problem. This means that, in his view, there is an inherent a priori uncertainty concerning the very identity of the observer within the quantum framework. To elegantly reconcile this pervasive subjectivity with the scientific imperative of objectivity, Carter introduces a crucial conceptual distinction. He differentiates between the concept of a material observer, a physical entity, such as a human being, and an abstract perceptor. The perceptor, in Carter's framework, represents the fundamental locus of consciousness, whose chances of identification with a particular material observer need to be precisely prescribed by a suitable, and indeed micro-level, anthropic principle. He boldly proposes that this prescription should be done by an entropy ansatz, a profound hypothesis according to which the relevant microanthropic weighting for a particular quantum branch is taken to be directly proportional to the logarithm of the relevant number of Everett-type branches. This proposal suggests that the probability of our existence in a particular branch is tied to the amount of information or complexity that branch allows. As these profound concepts of quantum reality and self-awareness drift through your mind, feel the gentle pull towards the depths of intellectual repose, where understanding and peace merge. The final part of the book, Part 4, broadens its scope to address the more general philosophical and epistemological aspects of the multiverse proposal. This section delves into profound questions concerning the very nature of scientific knowledge, the limits of empirical inquiry, and the delicate boundaries between science and metaphysics. It is within these chapters that the crucial issue of the multiverse's scientific legitimacy is rigorously debated. The contributions in this part are notably written from a different intellectual standpoint than those in the preceding sections. Whereas the contributors in parts 1 through 3 are, for the most part, generally positive or at least open-minded about the idea of the multiverse, presuming that their intellectual engagement stems from a belief in its potential validity. Many of the contributors in Part 4 adopt a more critical stance. Their critiques range from preferring more traditional theological interpretations of the observed anthropic coincidences to outright dismissing multiverse speculations as fundamentally transcending the boundaries of legitimate science altogether. The most incisive and deeply skeptical of these critics is Lee Smolin, a prominent and often provocative theoretical physicist. His chapter, Scientific Alternatives to the Anthropic Principle, stands as the longest and arguably most comprehensive contribution in the entire volume. It plays a truly crucial role in meticulously bringing together and rigorously articulating all the major criticisms leveled against the multiverse proposal. Smolin begins his powerful argument by contending that the anthropic principle, in its commonly invoked forms, cannot genuinely be considered a part of rigorous science. His core reason: it fundamentally fails to yield any empirically falsifiable predictions. He meticulously dissects various claims of successful anthropic predictions, arguing that they are either uncontroversial applications of well-understood selection principles operating within a single universe, e.g., we must live on a planet not in empty space, or that they depend solely on observed facts that are logically independent of any assumptions about the existence of life or intelligence. The principle of mediocrity, a concept first formulated by Alex Vilenkin,
which posits that we should expect to be typical observers within the multiverse, is also subjected to Smolin's rigorous scrutiny. He claims it is inherently unreliable, demonstrating how arguments based on it, even when leading to seemingly true conclusions, can be easily manipulated to yield demonstrably false conclusions by merely introducing reasonable changes in the specification of the ensemble against which we are assumed to be typical. However, despite this overarching critique, Smolin then offers a crucial constructive path forward. He demonstrates that it is indeed still possible to formulate rigorously falsifiable predictions from multiverse theories, but only if the ensemble predicted by the theory possesses certain specified properties that differentiate it from a random ensemble. In this context, he emphasizes his own favored multiverse proposal, cosmological natural selection. This audacious and innovative proposal posits the continuous generation of descendant universes through the profound process of black hole formation, where universes reproduce and their parameters are subtly mutated. Smolin argues that his cosmological natural selection proposal, in its current formulation, remains unfalsified, yet is remarkably vulnerable to falsification, making it a prime example of a proper scientific theory. He concludes by discussing the profound consequences of his arguments for recent applications of the anthropic principle within the context of string theory, particularly those explored in Part 3 of this volume, challenging their scientific rigor. Let the intellectual clarity and reasoned debate of these arguments guide your mind towards a deeper sense of peace and understanding. The pursuit of truth, even when challenging, is its own reward and a path to profound tranquility. Several other compelling contributions within this concluding part of the book also directly address the fundamental question of whether the multiverse proposal genuinely holds scientific respectability. However, it's crucial to note that not all of these contributions share Lee Smolin's ultimately negative conclusion regarding its scientific legitimacy. In making predictions in a multiverse conundrums, dangers, coincidences, Anthony Aguirre, a thoughtful and insightful cosmologist, acknowledges at the outset that the audacious notion of many universes, each endowed with different physical properties, indeed offers a powerful and elegant answer to the profound question of why our particular universe appears so astonishingly hospitable to the existence of life. He further recognizes that this compelling notion naturally arises from current, cutting-edge ideas in eternal inflation and the intricate framework of M/string theory. However, Aguirre then pivots to pose the central challenge: how do we as scientists actually test a multiverse theory? And, perhaps even more fundamentally, when confronted with a multitude of possibilities, which of the many universes do we compare to our own observed reality? His chapter meticulously enumerates what would appear to be the essential ingredients, the foundational prerequisites, for rigorously making testable predictions within this complex framework. He then thoughtfully outlines different strategic approaches one might adopt within this challenging intellectual landscape, and subsequently engages in a candid discussion of some of the inherent difficulties and potential dangers that permeate these approaches. Finally, he delves into the intriguing question of whether the predictions of multiverse theories, despite their individual complexities, share any general, overarching qualitative features. The crucial and recurring issue of testing a multiverse hypothesis also features prominently in the insightful contribution of George Ellis, a distinguished cosmologist and philosopher, whose chapter is titled Multiverses: Description, Uniqueness, and Testing. Ellis, known for his rigorous and often skeptical approach to grand cosmological claims, ultimately concludes that the multiverse proposal, in its current forms, doesn't, in fact, constitute proper science. He begins by emphasizing that any coherent description of a multiverse is fundamentally determined by two successive specifications. First, a meticulous outlining of a possibility space, the complete set of potentially existing universes and their inherent characteristics. And second, the definition of a distribution function over this space, which specifies which of these possibilities are actually realized and with what frequency. Ellis articulates his skepticism by highlighting a pervasive lack of uniqueness at both of these crucial stages. He argues that we are, at present, unable to either observationally determine the specific nature of any multiverse that is claimed to exist, or to experimentally validate any claimed causal mechanism that would, in theory, create such an ensemble. While he concedes that multiverses may offer a degree of explanatory usefulness in accounting for phenomena like fine-tuning, he rigorously maintains that arguments for their existence are, in their deepest essence, ultimately, of a philosophical nature. Ellis isn't by any means an antagonist of metaphysics. Indeed, he has written extensively and profoundly on philosophical and theological issues related to cosmology. However, he firmly believes that philosophical speculation, however profound, should not be confused with rigorous scientific inquiry, which demands empirical testability and falsifiability. The profound importance of establishing a robust and coherent, probabilistic basis for assessing the various multiverse scenarios is also thoughtfully highlighted by Don Page, a distinguished theoretical physicist. His chapter is titled Predictions and Tests of Multiverse Theories. Page, who, like Ellis, holds a religious persuasion, nevertheless arrives at a somewhat different and arguably more optimistic conclusion regarding the scientific testability of multiverse theories. He begins by acknowledging that a multiverse, by its very definition, usually encompasses parts that are, by their nature, unobservable to us. However, he argues that if the overarching theory that posits the multiverse also includes suitable measures for observations, that is, a rigorous way to assign probabilities to what we might perceive, then what is observable can, in principle, be coherently explained and even predicted by the theory, even if it contains unobservable elements. Thus, in Page's view, genuinely good multiverse theories are, indeed, testable. For the purpose of rigorous Bayesian comparisons of different theories that predict more than one observation, Page introduces and meticulously develops the crucial concept of typicality. This typicality is defined as the likelihood given by a theory that a random result of an observation would be at least as extreme, in a statistical sense, as the result of one's actual observation. He also intricately links this concept to the various interpretations of quantum theory, particularly the many worlds interpretation. Page notes that some multiverse theories can be regarded as pertaining to a single, overarching, quantum state of the universe. While such a quantum state rigorously obeys certain fundamental equations, this immediately raises a deeper question: why do those specific equations apply? Other multiverse theories, however, can be regarded as pertaining to more than one quantum state existing in a larger ensemble. These theories, in turn, raise another profound question. Why is the measure for the set of different universes the statistical weighting such that our specific observations are not found to be too atypical? This delves into the heart of selection effects and the probability of our existence. Let these intricate arguments about testability and probability gently carry your thoughts, inviting a deeper, more settled state of mind, guiding you to rest. The next two contributions courageously tackle the profound religious issues explicitly and directly. Are anthropic arguments involving multiverses and beyond legitimate? Is a particularly welcome and unique contribution, precisely because it comes from William Stuger, a scholar who seamlessly bridges two formidable intellectual realms. He is both a working scientist, deeply engaged in cosmological research, and profoundly a Jesuit priest. After offering a meticulous review of the historical development and various formulations of the anthropic principle, Stuger delves into a rigorous discussion of the two main versions of its strong form: the postulation of a divine creator who designed the cosmos, or the concept of a multiverse as a natural explanation. The latter, he notes, strives to confine anthropic arguments squarely within the realms of legitimate science, invoking an actually existing ensemble of universes or distinct universe domains. Stuger then critically examines the scientific status of this multiverse proposal, briefly indicating the fundamental criteria that are necessary for both the precise definition and the empirical testability of a multiverse. He subsequently describes some purely scientific applications of anthropic arguments, demonstrating their utility within established scientific frameworks. After thoughtfully discussing the key philosophical presumption upon which the strong anthropic principle fundamentally rests, namely that the universe could have been different, and its intricate relationship to the elusive concept of a possible final theory of everything, he summarizes his main conclusions concerning the two transcendent explanations of the strong anthropic principle, divine creation versus a multiverse. Stuger ultimately concludes that even if the existence of a multiverse were rigorously proved, he would not regard this as providing an ultimate explanation for cosmic suitability. In his view, it would certainly not, in any logical sense, exclude the existence of God, suggesting that a creator could be the author of the multiverse itself. However, he wisely cautions that such ultimate considerations inevitably transcend the boundaries of science itself, venturing into the realm of philosophy and theology. As suggested by its evocative title, The Multiverse Hypothesis, a Theistic Perspective, the chapter by Robin Collins also explicitly adopts a theological stance, offering a unique and deeply considered viewpoint. Collins begins by acknowledging a common intellectual alignment. Many individuals, particularly those advocating for naturalistic explanations, have promoted the multiverse hypothesis as the primary atheistic alternative to a theistic explanation for the astonishing fine-tuning of the cosmos, its remarkable suitability for the existence of life. However, Collins, with a nuanced theological argument, contends that the multiverse hypothesis is, in fact, entirely compatible with theism. Indeed, he goes further, claiming that the very concept of the generation of many universes through some underlying physical process fits remarkably well with the traditional theological belief that God is infinitely creative, a divine abundance manifesting in a multiplicity of worlds. He notes that even such a process of multiverse generation would, itself, have to be structured in precisely the right way, with exquisitely precise meta-laws, in order to produce even one life-sustaining universe. Consequently, this theistic version of the multiverse hypothesis does not, in his view, completely avoid the subtle yet persistent suggestion of design at a deeper level. Finally, Collins considers other compelling pointers that suggest a theistic explanation for the universe, such as the inherent beauty and profound elegance of the fundamental laws of nature. He then argues that Max Tegmark's bold multiverse hypothesis, which posits that all possible laws of nature are, in some profound sense, actualized in some universe or another, the Level 4 multiverse, does not adequately account for this specific aspect of the laws of nature, namely, their observed elegance and beauty. There are, of course, alternative and often exotic interpretations of the multiverse hypothesis that are neither strictly anthropic nor overtly theistic. One compelling example of this, which we briefly encountered earlier, is Lee Smolin's cosmological natural selection proposal, where universes reproduce and evolve. Another, perhaps even more exotic version, a concept rigorously explored by Nick Bostrom, though not elaborated upon in this specific volume, is the startling philosophical proposition that our entire universe might in fact be a sophisticated computer simulation. This audacious and speculative theme forms the captivating subject of John Barrow's chapter, titled Living in a Simulated Universe. In this intriguing contribution, Barrow meticulously explains why, if we indeed reside within a simulated reality, we might reasonably expect to observe occasional glitches or subtle, gradual drifts in the supposed constants and fundamental laws of nature over vast cosmic timescales. He even tantalizingly suggests that there might already be some faint, ambiguous evidence for this from current astronomical observations, although he is quick to caution that the interpretation of these subtle effects remains highly controversial and far from conclusive. Finally, another thought-provoking interpretation of the anthropic tunings offering a unique and often skeptical perspective is provided in the concluding chapter by Paul Davies, Universes Galore, Where Will It All End? Davies, a physicist renowned for his philosophical acumen, articulates a cautious approach to the multiverse concept. He argues that, while a little bit of multiverse is good for you, meaning that certain, well-defined multiverse ideas can be scientifically fruitful, invoking multiverse explanations indiscriminately and willy-nilly constitutes a seductive, yet ultimately perilous, slippery slope. Followed to its ultimate logical extreme, he contends, such unbridled speculation leads to conclusions that are, at best, bizarre, and at worst, verging on the absurd. After meticulously reviewing several of the inherent shortcomings and potential pitfalls of indiscriminate multiverse explanations, including the intriguing concept of a simulated multiverse, as discussed by Barrow, Davies courageously challenges the perceived false dichotomy that fine-tuning necessarily requires the existence of either a multiverse or some form of traditional cosmic architect. Instead, he explores the compelling possibility of a third way, an alternative intellectual path that involves a radical reappraisal of the very notion of physical law itself. To illustrate this audacious concept, he presents a captivating toy illustration drawn from the fascinating mathematical world of cellular automata, suggesting that laws might be emergent or self-generating rather than divinely imposed or arbitrarily chosen.
As these profound and diverse arguments gently echo in the spacious chambers of your mind, allow their complexity to dissolve, leaving behind only the pure sensation of wonder and the profound tranquility that precedes the deepest slumber. You are now immersed in the very fabric of cosmic thought, gently drifting towards the peace of the night.